हेलो दोस्तों, आज हम फिजिक्स क्लास 12 पार्ट 1 का मैराथन सेशन स्टार्ट करने जा रहे हैं। इसमें हम चैप्टर 1 से लेकर चैप्टर 7 तक कंप्लीट कवर करेंगे और जो बाकी के चैप्टर्स हैं 8 से लेकर 14 तक, उन्हें हम पार्ट 2 में कवर करेंगे। इससे पहले मैं आपको बता दूं, मैंने जूलॉजी और बॉटनी क्लास 11th प्लस 12th कंप्लीट करवा दिया है और फिजिक्स क्लास 11th का भी फुल मैराथन हो चुका है। और हाँ, अगर आप ये वीडियो 14 अप्रैल के बाद देख रहे हो तो टैब तक फिजिक्स पार्ट 2 भी आ चुका होगा। वैसे मेन प्लेलिस्ट का लिंक डिस्क्रिप्शन में डाल दूंगा, जहां से आप इजीली सारी मैराथन वीडियोस देख सकते हो। सब्जेक्ट के आईपैड हैंडरिटन नोट्स भी अवेलेबल है, सिर्फ 95 रुपये में। कॉन्टैक्ट नंबर डिस्क्रिप्शन में दिया हुआ है, वहां से आप सारी डिटेल्स ले सकते हो। बस एक छोटी सी रिक्वेस्ट है, प्लीज इस वीडियो का टाइम स्टैम्प कॉमेंट सेक्शन में लिख देना ताकि और स्टूडेंट्स की हेल्प हो जाए। और सिर्फ इस वीडियो का ही नहीं, जितने भी मैराथन वीडियोस हैं उनके टाइम स्टैम्प्स भी अगर आप कमेंट में डाल दो तो सबको बहुत फायदा मिलेगा। तो चलो जर्नी को शुरू करते हैं, फिजिक्स पार्ट 1 की जर्नी। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी कॉलम्स लॉ और गॉसेस लॉ जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम इलेक्ट्रिक फील्ड और इलेक्ट्रिक पोटेंशियल के बीच का फर्क समझते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त, इस वीडियो में हम इस चैप्टर के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और इस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इंपॉर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। इससे पहले वाली फिजिक्स की वीडियो भी हमने ऑलरेडी कंप्लीट कर दी है, जिसे तुम प्लेलिस्ट में जाकर चेक कर सकते हो। इस लेक्चर के हैंडरिटन आईपैड नोट्स का लिंक डिस्क्रिप्शन में है और पूरी प्लेलिस्ट भी वहां मिल जाएगी। ओके।
Introduction. Amit and Sanjay are planning to purchase some articles from the market. For this, Sanjay is ready and waiting for Amit. Amit is combing his hair. After combing, when he puts the comb on the table and again picks the comb, then he gets surprised. He observes that some pieces of a paper are stuck to the comb. He shakes the comb well, but only few falls down, while others are still stuck to it. He asks Sanjay that why paper pieces are attracted towards the comb. Sanjay tells him that it was due to the attraction of charges. When you comb the hair, then comb gains charge due to rubbing. When this comb comes in contact with the paper, then opposite charge gets developed on the paper, and due to this, they both attract each other. Students, electric charges are present everywhere around us. Today we will study about the electric charges and fields. Objectives. At the end of this lesson, you'll be able to define electric charge, define conductors and insulators, know about charging by induction, understand basic properties of electric charge, define Coulomb's law, calculate forces between multiple charges, describe electric field, draw electric field lines, know about electric flux and electric dipole, analyze dipole in uniform external field, calculate continuous charge distribution, define Gauss's law and its applications. Electric charge. There are two kinds of charges, positive charge and negative charge. Like charges repel each other and unlike charges attract each other. If two glass rods rubbed with silk cloth are brought close to each other, they repel each other. If two plastic rods rubbed with silk cloth are brought close to each other, they repel each other. If one glass rod and one plastic rod is rubbed with silk cloth are brought close to each other, they attract each other. Electric charge is a scalar quantity. SI unit of charge is coulomb. Every neutral object contains an equal number of electrons and protons. When the number of electrons and protons are not equal, the object possesses a net positive or negative charge. Conductors and insulators. Materials are classified in terms of their ability to allow electric charge to move or be conducted through them. Conductors are materials that readily conduct electric charge. Metals are good conductors, for example, copper, silver, aluminium, and gold. In a metallic conductor, the number of free electrons that can move throughout the material is large. The exact number of electrons detached from each atom depends on the nature of the material. Insulators are materials that do not readily allow electric charge to move. Examples of good insulators are rubber, wood, glass, and mica. In an insulator, there are no free electrons. All the electrons are bound to their parent atoms and conduction of charge is not possible. Charging by induction. The process of giving one object a net electric charge without touching the object to a second charged object is called charging by induction. When a conductor is connected to the earth by means of a conducting wire, it is said to be grounded or earthed. Let's take an example to understand this phenomenon. Bring a negatively charged rod near an isolated uncharged sphere. As a result, the part of the sphere nearest the rod becomes positively charged and the part farthest away becomes negatively charged. Connect grounding wire to the sphere. Some of the electrons will now leave the sphere and move to the earth. Remove the ground connection. The conducting sphere is left with an excess of induced positive charge. Remove the rubber rod. The conducting sphere is now left with a net positive charge. Basic properties of electric charge. Additivity. The total charge of a system is the algebraic sum of all individual charges distributed over different parts of the system. For example, the total charge of a system containing 4 charges, 2 coulomb, minus 5 coulomb, minus 6 coulomb, and 4 coulomb is equal to minus 5 coulomb. Conservation of charge. The total charge of an isolated system remains constant during any process. Charge can be transferred from one body to another, but it can neither be created nor destroyed. For example, grounding of the charge. Quantization. Any charged body has a total charge that is an integral multiple of a certain smallest amount of a charge E. The smallest amount of free charge E that has been discovered is the charge on an electron or a proton having magnitude 1.60 into 10 raised to the power minus 19 coulomb. Any charge Q on an object can always be expressed as Q is equal to NE, where N is an integer. Coulomb's law. The magnitude of the electric force exerted by one point charge on another point charge is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. The force is directed along the line joining the two charges. The magnitude F of the force between 2 point charges and separated by a distance r can be expressed mathematically as F is equal to K into mod Q1 into mod Q2 divided by r square. Here, K is a constant of proportionality. For vacuum and in SI system, Coulomb's law becomes F is equal to 1 upon 4 pi epsilon naught multiplied by mod Q1 into mod Q2 divided by r square. Forces between multiple charges. Superposition principle. For an assembly of charges, the total force on a particular charge is the vector sum of the individual Coulomb forces exerted on it by all other charges, the force between any two charges being unaffected by the presence of other charges. For a system of n charges, Q1, Q2, Q3 and so on till Qn, the total force F1 on charge Q1 due to all other charges Q2, Q3, Q4 and so on till Qn is F1 is equal to F12 plus F13 plus F14 and so on till F1n. This equation can be written as example. Let's take an example on Coulomb's law. Find the force on the center charge in given figure. Let's see the solution. Let F1 be the magnitude of the force with which charge Q2 is attracted towards Q1. We know that F1 is equal to 1 upon 4 pi epsilon naught multiplied by Q1 Q2 upon R square. Put the values in this equation. We get F1 is equal to 45 into 10 raised to the power minus 3 Newton, which is equal to 0.045 Newton. F2 is the magnitude of the force with which charge Q2 is attracted towards Q3. Put the values in the above equation. We get F2 is equal to 16.875 into 10 raised to the power minus 3 Newton, which is equal to 0.0169 Newton. Net force F experienced by Q2 is directed towards Q1 and is given by F is equal to F1 minus F2, which equals 0.045 minus 0.0169 Newton, which is equal to 0.0281 Newton. Electric field. There is a region of space around a charge or a system of charges within which other charged particles experience electrostatic forces. This region is known as an electric field. The electric field E at a point is defined as the electric force F experienced by a small positive test charge Q not placed at that point divided by the charge itself. E is equal to F upon Q naught. The electric field E is a vector having the same direction as the force F on a positive test charge. The SI unit of electric field is Newton per Coulomb. The electric field at a point is given by E is equal to 1 upon 4 pi epsilon naught multiplied by Q upon R square into R cap. The superposition principle holds when calculating the electric field due to a group of point charges. E is equal to E1 plus E2 plus E3 and so on till En. This equation can be written as E is equal to summation from I equals 1 to n of 1 upon 4 pi epsilon naught multiplied by Qi upon RPI square into RPI cap. Electric field lines. Electric field lines are a kind of map that gives the direction and indicates the strength of the electric field at various places. The field lines always begin on a positive charge and end on a negative charge or at infinity in the case of a single charge. The number of field lines leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. No two field lines can cross each other. The relative closeness of the field lines indicates the relative strength of the electric field in various regions. Electric flux. Electric flux phi E is a measure of the number of electric field lines cutting through a hypothetical surface in an electric field. For a planar surface of area S immersed in a uniform electric field E, the electric flux is defined as phi E is equal to Es cos theta. When E is perpendicular to the surface, theta is equal to 0 degree and phi E is equal to Es, a maximum value. In this situation, a maximum number of field lines pass through the surface. When E is parallel to the surface, theta is equal to 90 degree and phi E is equal to 0. In this case, no field lines pass through the surface. For an arbitrary closed surface immersed in a general electric field, the electric flux is defined as an integral over the surface of E cos theta. The SI unit of electric flux is Newton meter square per Coulomb. Electric dipole. A pair of 2-point charges, minus q and plus q, having the same magnitude but opposite signs, separated by a distance 2a, is called an electric dipole. The line joining the two charges, minus q and plus q, is called the dipole axis. The electric dipole moment P of an electric dipole is a vector pointing from the charge minus q towards the charge plus q and having magnitude equal to the charge q times the distance 2a between the charges. P is equal to 2aq p cap. Dipole in an uniform external field. Let's consider a dipole placed in a uniform electric field E, with the dipole moment P making an angle theta with E. Force on charge plus q is QE and on charge minus q is minus QE. Since the forces are equal and anti-parallel, the net force on the dipole is zero. However, the two forces QE and minus QE form a couple. Magnitude of the torque is equal to magnitude of each force into arm of the couple. This equation can be written as tau is equal to cross product of P and E. Continuous charge distribution. The electric force on a point charge q due to a charge distribution can be conveniently calculated by assuming the charge distribution to be a continuous one. Calculation procedure. Divide the charge distribution into infinitesimal elements. Find the force on charge q due to one such element dq, assuming it to be a point charge. The resultant force on charge q is obtained by the integration of the field contributions due to all other charge elements of the charge distribution. Linear charge density, lambda. This term is used when the continuous charge distribution is along a line and is defined as the total charge per unit length of the line. Its SI unit is coulomb per meter. Surface charge density, sigma. This term is used when the continuous charge distribution is over a surface and is defined as the total charge per unit area of the surface. Its SI unit is coulomb per meter square. Volume charge density, rho. This term is used when the continuous charge distribution is over a three-dimensional region and is defined as the total charge per unit volume of the region. Its SI unit is coulomb per meter cube. Gauss's law. Gauss's theorem. The electric flux phi E through a Gaussian surface is equal to the net charge Q enclosed by the surface divided by epsilon naught, the permittivity of free space. Gauss's theorem is used to compute the charge inside a closed surface if E is known for all points on the surface. Application of Gauss's law. Field due to an infinitely long straight uniformly charged wire. As a Gaussian surface, we choose a circular cylinder of radius r and length L with its axis along the wire. If lambda is the linear charge density of the wire, the charge within the Gaussian surface is L lambda. We know that phi E is equal to integration of a closed surface of E dot ds, which equals to product of E and 2 pi RL, where 2 pi RL is the area of the curved surface of the cylinder. According to Gauss's theorem, we get electric field at any point at a radial distance r from the wire is equal to lambda divided by 2 pi r epsilon naught. Field due to a uniformly charged infinite plane sheet. As a Gaussian surface, we consider a circular cylinder of cross-sectional area A and height 2r with its axis perpendicular to the sheet. If sigma is the surface charge density of the sheet, the charge enclosed by the Gaussian surface is L sigma. We know that phi E is equal to integration over closed surface of E dot ds, which is equal to product of 2A and E. According to Gauss's theorem, we get electric field at any point at a radial distance r from the wire is equal to sigma divided by 2 epsilon naught. Field due to a uniformly charged thin spherical shell. To find the electric field at a point distant r from the center of the sphere of radius r, we choose a spherical Gaussian surface of radius r concentric with a charged sphere. If a rho is volume density of charge in the solid sphere, the total charge in the sphere is given by Q is equal to 4 upon 3 product of pi r cube, and rho. Case 1. For points outside the solid sphere, r is greater than r. The electric field at any point distant r from the center of the solid sphere is equal to 1 upon 4 pi epsilon naught multiplied by q upon r square. Case 2. For points inside the solid sphere, r is smaller than r. The electric field at any point distant from the center of the solid sphere is equal to 1 upon 4 pi epsilon naught multiplied by rq upon r cube. Did you know? During rubbing, a body which has lower work function loses electrons and becomes positively charged. A body having higher work function becomes negatively charged by gaining electrons. Positron is a particle whose mass is the same as that of an electron. Positron has a positive charge of the same magnitude as that of the negative charge on an electron. Recently, the existence of particles of charge 1 upon 3e and 2 upon 3e has been postulated. These particles are called quarks. Summary. Let us summarize what we have learned. Like charges repel each other and unlike charges attract each other. The process of giving one object a net electric charge without touching the object to a second charge object is called charging by induction. Any charged body has a total charge, that is, an integral multiple of a certain smallest amount of charge E. The magnitude of the electric force exerted by one point charge on another point charge is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. The force is directed along the line joining the two charges. For an assembly of charges, the two force on a particular charge is the vector sum of the individual Coulomb forces exerted on it by all other charges, the force between any two charges being unaffected by the presence of other charges. The region of space around a charge or a system of charges within which other charged particles experience electrostatic forces is known as an electric field. Electric flux is a measure of the number of electric field lines cutting through a hypothetical surface in an electric field. The electric flux through a Gaussian surface is equal to the net charge enclosed by the surface divided by the permittivity of free space.
तो मेरे प्यारे दोस्तों, ये था इलेक्ट्रिक चार्जेस एंड फील्ड्स का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी इलेक्ट्रिक पोटेंशियल और कैपेसिटेंस जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम सीरीज और पैरेलल कैपेसिटर्स के फॉर्मूलास देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम इस चैप्टर के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और इस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इम्पोर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। इससे पहले वाली फिजिक्स की वीडियो भी हमने ऑलरेडी कंप्लीट कर दी है, जिसे तुम प्लेलिस्ट में जाकर चेक कर सकते हो। इस लेक्चर के हैंड रिटन आईपैड नोट्स का लिंक डिस्क्रिप्शन में है और पूरी प्लेलिस्ट भी वहां मिल जाएगी। ओके।
Introduction. Prince and his father are standing at the window side and viewing outside. It is a rainy weather. Suddenly, lightning occurs and falls down. Prince observed that the tree on the road catches fire due to lightning. He asked his father that why tree catches fire and the car remains safe on the road. His father replied him that it's due to electrostatic shielding. When lightning falls on the car, then all the charge flows through the other surface of the car and then grounded. But in case of the tree, it does not happen. Students, you must be more curious to know and learn this fact and topics. So let's study more about this in the chapter Electrostatic Potential and Capacitance. Objectives. At the end of this lesson, you'll be able to define electrostatic potential, calculate potential due to a point charge, system of charges and an electric dipole, define principle of superposition for electric potential, define equipotential surface, define potential energy, calculate potential energy of a system of charges and electrical dipole, know electrostatics of conductors, explain electrostatic shielding. Electrostatic potential. Electric potential of an electric field at a given point is defined as the amount of work done in bringing a unit positive charge from infinity to that point. Electric potential is measured in volt. If 1 joule work is done in moving plus 1 coulomb charge from infinity to a point in an electric field, then the potential at that point is 1 volt. The potential difference between 2 points A and B is given by VAB equals WBA upon Q naught. The potential difference between 2 points in an electric field is equal to the amount of work done in moving a unit positive charge from lower to higher potential point. Potential due to a point charge. A point charge plus Q is situated at a point O in space. This charge creates its own electric field E around itself. We have to calculate the potential of this electric field at point A. We consider two very close points P and Q on the line OA. The total work done in moving plus 1 coulomb charge from infinity to point R is given by W is equal to 1 upon 4 pi epsilon naught multiplied by Q upon R. This amount of work is the potential of the electric field created by the point charge plus Q at a distance R from Q. We can show in the graph that as R increases, the potential falls down hyperbolically. If point A is at higher potential than point B, then the potential difference between the 2 points is given by VAB equals VA minus VB. Put the values of VA and VB, we get VAB is equal to Q by 4 pi epsilon naught multiplied by 1 upon A minus 1 upon B. Principle of superposition for electric potential. Let us consider 2 point charges plus Q1 and plus Q2. Take any 2 points A and B in the combined electrostatic field of 2 charges Q1 and Q2. Choose a curve L between A and B. We know that VB minus VA is equal to minus integration from A to B of E vector dot dl vector. But according to principle of superposition of electric fields, E vector is equal to E1 vector plus E2 vector. Therefore, VB minus VA is equal to minus integration from A to B of E1 vector plus E2 vector dot dl vector. So, electrostatic potential differences are additive. If A is taken to infinity, then V is equal to sum of minus integration from infinity to B of E1 vector dot dl vector and minus integration from infinity to B of E2 vector dot dl vector. So, the electrostatic potential at B is the scalar sum of potential at B due to charge Q1 alone and potential at B due to charge Q2 alone. This result is applicable for any number of charges. Potential due to an electric dipole. We consider a dipole with two charges, plus Q and minus Q, separated by a distance 2L from each other. We calculate the potential of the field due to this dipole at different points. Potential at an end-on point. Consider an axial point P at a distance r from center O of dipole on the side of plus Q. The potential at P due to plus Q is given by V positive equals 1 upon 4 pi epsilon naught multiplied by Q upon r minus 1. The potential at P due to minus Q is given by V negative is equal to 1 upon 4 pi epsilon naught multiplied by minus Q upon r plus 1. The total potential at P is obtained by having direct addition of the two and is given by VE is equal to 1 upon 4 pi epsilon naught multiplied by P upon r square. This shows that the potential along the axis of dipole falls inversely with the square of distance. Potential at broadside point due to an electric dipole. Consider a point P on the equatorial line at a distance r from the center of dipole. The potential at P due to plus Q is given by V positive equals 1 upon 4 pi epsilon naught multiplied by Q upon under root r square plus L square. The potential at P due to minus Q is given by V negative equals 1 upon 4 pi epsilon naught multiplied by minus Q upon under root r square plus L square. The total potential at P is obtained by having direct addition of the two and is given by VB equals 0. This shows that the potential at any broadside on point is 0. Potential in plane of an electric dipole. Consider a point P on the plane of dipole at a distance r from center O of dipole and PO makes an angle theta with the axis of dipole AB. The distances of P from A and B are R1 and R2 respectively. The total potential at P is given by V equals Q upon 4 pi epsilon naught multiplied by R1 minus R2 upon R1 R2, which is equal to 1 upon 4 pi epsilon naught multiplied by P cos theta upon r square. This is a generalized expression for representing the potential of a field of short dipole at any point on the plane of the dipole. Potential due to a system of charges. Consider the point charges Q1, Q2, Q3 and so on till Qn at distances r1, R2, R3 and so on till Rn respectively from a point of observation P. The resultant potential at P due to all the charges is the algebraic sum of the potentials at P due to individual charges. This is because electric potential is a scalar quantity. The resultant potential at P is given by V as V1 plus V2 plus V3 and so on till Vn. Equipotential surfaces. An equipotential surface is the locus of points at which the potential due to a charge distribution is same. No work is done in moving a charge from one point to another along an equipotential surface. In a point charge for a given radius, electric potential is same, and the equipotential surfaces are spherical surfaces centered on the charge. Electric field lines created by any system of charges are always perpendicular to the associated equipotentials. Example on equipotential surfaces. Let's take an example on equipotential surfaces. An infinite thin plane sheet of charge density 10 raised to the power minus 8 coulomb per meter square is held in air. How far apart are two equipotential surfaces whose potentials differ by 5 volt? Let's see the solution. We know that electric field intensity E is equal to sigma upon 2 epsilon naught. Since E does not depend upon the distance from the plane sheet, therefore E is constant for the given problem. If delta x meter is the separation between two equipotential surfaces which differ in potential by delta V, then E is equal to delta V upon delta x. We evaluate the value of delta x as 2 epsilon naught delta V divided by sigma. By putting the values in the equation and evaluating, we get the value of delta x is equal to 8.85 millimeter. Potential energy. The potential energy of a charge Q present at a point in an electric field is equal to Q times the potential of the field at that point. U is equal to QV. The unit of potential energy is joule. Bringing of any charge Q from infinity to a point A in an electric field E will require a work WA to be done on the charge, which is stored in the charge Q as its potential energy. UA is equal to QVA. The electric potential energy of a system of stationary charges is the work that has to be done in bringing these charges from infinity to the points near each other to form the system. Potential energy of a system of charges. The potential energy of a system of point charges is the work required to assemble this system of charges by bringing them in from an infinite distance. Potential energy of the system of two-point charges. The electrostatic potential energy of the system of two-point charges is given by U as 1 upon 4 pi epsilon naught multiplied by Q1 Q2 upon R12, where Q1 and Q2 are the electric charges of the 2 points. R12 is their separation distance. Potential energy belongs to the system as a whole and not to any individual charges. Note that the electric potential energy is the product of charge and electric potential. Potential energy of the system of 3-point charges. The potential energy of the system of 3-point charges is the energy required to assemble the system of 3-point charges from an initial situation in which 3 charges are infinitely far apart. The procedure for calculating this electric potential energy is to calculate the potential energy for every pair of charges separately and to add the results algebraically. The electrostatic potential energy of the system of 3-point charges is given by U is equal to 1 upon 4 pi epsilon naught multiplied by Q1 Q2 upon R12 plus Q2 Q3 upon R23 plus Q1 Q3 upon R13, where Q1 Q2 and Q3 are the electric charges of the 3 points, and R12, R13 and R23 are their separation distances. Potential energy of an electric dipole in an external field. Consider an electric dipole of dipole moment P is placed in a uniform electric field E. The dipole experiences two equal and opposite forces plus QE and minus QE at its ends forming a couple. Magnitude of the torque on the dipole is equal to magnitude of the force into arm of the couple. Tau is equal to QE into 2L sine theta, which is equal to PE sine theta. Work done in rotating the dipole through a small angle d theta is equal to tau d theta, which is equal to PE sine theta d theta. Total work done in rotating the dipole from an initial orientation theta naught to the final orientation theta is W equals to minus PE cos theta minus cos theta naught. If the initial orientation theta naught is equal to 90 degrees, then W is equal to minus PE cos theta. This work is stored as potential energy. Thus, potential energy of the dipole is U as minus PE cos theta, which can be written as minus P dot E. Electrostatics of conductors. A conductor is said to be in electrostatic equilibrium if there is no net movement of charge within and on the surface of the conductor. The electric field is zero at all points in a conductor. The electric field just outside the surface of a charged conductor is perpendicular to the surface. Excess charges on an isolated conductor in an electrostatic condition reside entirely on its surface. Excess charges on an irregularly shaped conductor tend to accumulate at locations where the curvature of the surface is greatest. The electric potential is constant everywhere inside a conductor and equal to its value at the surface. Electrostatic shielding. The placing of a grounded metal screen or enclosure around a device to prevent electric fields from interacting is known as electrostatic shielding. It is the best way to protect some area in vacuum from the influence of external electric field. Electric field is zero inside a conductor of any shape in electrostatic shielding. If a conductor A kept at zero potential surrounds conductor B, then B is said to be electrically shielded by A from other electric systems. For example, in a thunderstorm accompanied by lightning, it is safer to be inside a bus or car rather than near a tree or open ground. Did you know? Volta had already created the electrophorus to create static electric charges and discovered methane. The volt was officially established in 1881 as an electrical potential of 1 joule per coulomb of charge. It is used around the world. The electric potential decreases in the direction of field and increases against the direction of electric field. Equipotential surfaces and electric lines of force constitute a mutually perpendicular network. Summary. Let us summarize what we have learned. The potential difference between 2 points in an electric field is equal to the amount of work done in moving a unit positive charge from lower to higher potential points. Electric potential of an electric field at a given point is defined as the amount of work done in bringing a unit positive charge from infinity to that point. Potential along the axis of dipole falls inversely with the square of distance. An equipotential surface is the locus of points at which the potential due to a charge distribution is the same. The electric potential energy of a system of stationary charges is the work that has to be done in bringing these charges from infinity to the points near each other to form the system. A conductor is said to be in electrostatic equilibrium if there is no net movement of charge within and on the surface of the conductor. The placing of a grounded metal screen or enclosure around a device to prevent electric fields from interacting is known as electrostatic shielding.
Introduction. Students, today we will study a new topic. Before further proceeding, I wanna ask you something. Do you know about this? Sir, it's a resistor. No, Ram, it's not a resistor. Anybody else? Okay,
I will tell you. This is a capacitor. It is used to store the electric energy. Now, I am taking two capacitors of 5 microfarad and making combinations from these. The equivalent capacitance value in this case is 2.5 microfarad. The equivalent capacitance value in this case is 10 microfarad. Sir, how the value of equivalent capacitance change by making changes in their combination? Good question, Ajay. Let me tell you. In series combination, the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. However, in parallel combination, the equivalent capacitance is equal to the sum of the individual capacitances. Students, today we will study more about this in chapter Electrostatic Potential and Capacitance. Objectives. At the end of this lesson, you will be able to define dielectrics, understand polarization in dielectrics, explain capacitors and capacitance, describe the parallel plate capacitor, analyze effect of dielectric on capacitance, know about combination of capacitors, calculate energy stored in a capacitor, understand Van de Graaff generator. Dielectrics. A dielectric is an insulating material like mica, glass or ceramic. Dielectric materials are of two types: polar and non-polar. Polar dielectric. Polar materials are composed of molecules that have permanent electric dipole moments. In a polar dielectric, the molecular dipoles are randomly oriented when no electric field is present. When an electric field is present, these dipoles experience a torque and tend to align with the electric field. Non-polar dielectric. Non-polar materials contain molecules that do not have permanent dipole moments. When a dielectric consisting of non-polar molecules are placed in an external electric field, the positive and negative charges of the molecule experience forces in opposite directions and become displaced relative to each other. The molecules are said to become polarized by the field and are called induced dipoles. Polarization in dielectrics. The extent to which the molecules of a dielectric become polarized by an electric field or oriented in the direction of the field is described by a vector quantity called the electric polarization. P is equal to Np, where N is equal to molecules per unit volume. P is equal to dipole moment of each molecule. For linear isotropic dielectrics, P is equal to product of Xi and E, where Xi is known as electric susceptibility of the dielectric. The positive ends of the dipoles remain unneutralized at the right surface and the negative ends at the left surface. The unbalanced charges are the induced charges due to the external field. The polarized dielectric is equivalent to two charged surfaces with induced surface charge densities positive sigma p and negative sigma p. Capacitors and capacitance. Capacitor. It is a device that consists of two conductors isolated from each other so that they can be given equal but opposite charges. Because of the charges minus Q and plus Q, the electric potential of the positive conductor exceeds that of the negative conductor by an amount V. The magnitude Q of the charge on each conductor is proportional to the potential difference V between them. Q is directly proportional to V, or Q is equal to CV. The proportionality constant C is called the capacitance of the capacitor. C is equal to Q by V. Capacitance. It is defined as the ratio of the magnitude of the charge on either conductor to the magnitude of the potential difference between them. The SI unit of capacitance is coulomb per volt, called farad. Capacitance of a spherical conductor. Let us consider a conductor in spherical shape of radius r. If this conductor is given a charge Q, the potential at its surface is given by V is equal to 1 upon 4 pi epsilon naught multiplied by Q upon R. It can be written as Q is equal to product of 4 pi epsilon naught R and V. We know that Q is equal to CV. On comparing above equations, the capacitance of the spherical conductor is given by C is equal to 4 pi epsilon naught R. This relation shows that the capacitance of spherical conductor is directly proportional to its radius. Larger is the radius, larger will be its capacitance. This expression is true for the conductor placed in air or vacuum. If the conductor is placed in an insulating medium with dielectric constant K, then the potential at its surface is given by V is equal to 1 upon 4 pi epsilon naught K multiplied by Q upon R. It can also be written as Q is equal to product of 4 pi epsilon naught K, R and V. Thus, C is equal to 4 pi epsilon naught KR. Hence, the capacitance of the conductor in the dielectric medium is K times its capacitance in air or vacuum. The parallel plate capacitor. A parallel plate capacitor consists of two parallel conducting plates separated by a distance that is small compared with the linear dimensions of the plates. Let the plates are in vacuum. If sigma is the magnitude of surface charge density on either plate, the electric field magnitude between the closely spaced parallel plates is equal to sigma upon epsilon naught, but sigma is equal to Q by A. Put the value of sigma in the above equation. We get E is equal to Q divided by epsilon naught A. Here, A is the area of each plate. The electric field between the plates is uniform and the potential difference between the plates is given by ED, which is equal to QD upon epsilon naught A. Here, D is the distance of separation of plates. The capacitance of a parallel plate capacitor is equal to Q upon V, which is equal to epsilon naught A upon D. Thus, we conclude that the capacitance of a parallel plate capacitor in vacuum is directly proportional to the area of one of the plates, inversely proportional to the separation of the plates, and independent of the charge on the capacitor. Effect of dielectric on capacitance. Consider a parallel plate capacitor having dielectric slab between capacitor plates. We consider A is equal to area of each plate. D is equal to plate separation. T is equal to thickness of dielectric slab. K is equal to dielectric constant of the dielectric. Sigma is equal to magnitude of surface charge density of the plates. Electric field between the capacitor plates but outside the dielectric is given by E naught is equal to sigma upon epsilon naught. Electric field within the dielectric medium is given by E is equal to sigma upon product of epsilon naught and K. Potential difference between the capacitor plates is given by V is equal to sigma upon epsilon naught multiplied by D minus T plus T upon K. Capacitance is given by C is equal to A epsilon naught divided by D minus T plus T upon K. When dielectric medium fills the entire space between the capacitor plates, then T is equal to D. It gives C is equal to Kc naught, where C naught is the capacitance in vacuum. K is equal to C upon C naught. The dielectric constant of a dielectric is the factor by which the capacitance of a capacitor increases from its vacuum value when the dielectric fills the entire space between the plates of the capacitor. Dielectric constant of the conductor. Let us consider an external uniform electric field E between two charged capacitor plates. Now a conducting slab is introduced in the field. The free electrons of metal are attracted towards the positive plate of E, and thus negative charges minus Q resides on the outer surface of metal slab that faces the positive plate of capacitor. Equal amount of charge plus Q will go on the outer surface of conductor that faces negative capacitor plate. Thus, outside the conductor slab the field remains E. Inside the conductor slab, a field EI is induced, equal in magnitude of E but opposite in direction. Thus, net resultant field inside the conducting slab ER is 0. It gives E upon ER is equal to K, which is equal to infinity. Hence, the dielectric constant of metal is infinite. Combination of capacitors. Two or more capacitors may be connected to each other in certain combination to produce an equivalent capacitance of any desired value. The equivalent capacitance C of a combination of capacitors is defined as the capacitance of a single capacitor for which the charge is the same as for the combination, when the potential difference V is the same. There are two types of combinations as follows: capacitors in series and capacitors in parallel. Combination of capacitors in series. In a series circuit, each capacitor gets the same charge as delivered by the battery, while the total EMF of the battery is distributed across different capacitors in inverse proportion to their capacitances. The reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on. The equivalent capacitance is always less than the smallest capacitance in the series. Combination of capacitors in parallel. In a parallel circuit, each capacitor gets the same potential difference equal to the EMF of the battery, while the total charge drawn out of battery is distributed in different capacitors in proportion to their capacitances. The equivalent capacitance is equal to the sum of the individual capacitances. C is equal to C1 plus C2 plus C3 plus so on. The equivalent capacitance is always larger than the largest capacitance in the parallel combination. Example on combination capacitors. Let's take an example on combination of capacitors. A technician has only two capacitors. By using these capacitors singly, in series or in parallel, he is able to obtain the capacitance of 4, 5, 20 and 25 picofarad. What are the capacitances of the two capacitors? Let's see the solution. We know that the resultant capacitance is maximum in parallel grouping. Cp is equal to C1 plus C2, or Cp is equal to 25 picofarad. Also, the resultant capacitance is minimum in series grouping. Reciprocal of Cs is equal to 1 upon C1 plus 1 upon C2, or Cs is equal to 4 picofarad. Thus, the maximum and minimum values are 25 picofarad and 4 picofarad respectively. Remaining values 20 picofarad and 5 picofarad represents the individual values of the two capacitors. Difference between series and parallel combination. In series combination, negative plate of one capacitor is connected to positive plate of the other and so on. Whereas in parallel combination, positive plates of all the capacitors are connected to one common terminal and negative plates are connected to another common terminal. In series combination, charge on each capacitor is same. Whereas in parallel combination, potential different across each capacitor is same. In series combination, V is equal to V1 plus V2 plus V3. Whereas in parallel combination, Q is equal to Q1 plus Q2 plus Q3. In series combination, reciprocal of Cs is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Whereas in parallel combination, Cp is equal to C1 plus C2 plus C3. In series combination, capacitors are connected in series to decrease the capacitance. Whereas in parallel combination, the capacitors are connected in parallel to increase the capacitance. Energy stored in a capacitor. The process of charging a capacitor consists of transferring charge from the plate at lower potential to the plate at higher potential. The work done in the charging process is stored as potential energy of the capacitor. At charging process, the potential difference between the plate is V is equal to Q by C. The additional work dW needed to transfer the next increment dQ of charge is given by dW is equal to V dQ, which is equal to Q by C into dQ. The total work required to charge the capacitor from its initial value 0 to a final value Q is given by integration of dW. Put the values of dW in the equation. We get W is equal to 1 upon C integration from 0 to Q of Q dQ, which equals to Q square upon 2C. Thus, the energy stored in the capacitor is given by U is equal to 1 by 2 CV square. Van de Graaff generator. A Van de Graaff generator is an electrostatic generator which uses a moving belt to accumulate very high voltages on a hollow metal globe on the top of the stand. The potential difference achieved in it can reach 5 megavolts. Principle: when a positively charged conductor is connected internally with a hollow conductor, the whole of its charge flows to the outer conductor. Potential difference between the spheres is given by VR minus VR is equal to Q upon 4 pi epsilon naught multiplied by 1 by R minus 1 by R. Working of Van de Graaff generator. The insulating belt is wound around two pulleys, one at ground level, one at the center of the large spherical conducting shell. This belt is kept continuously moving by a motor driving the lower pulley. It continuously carries positive charge sprayed onto it by a metal comb at the ground level to the top. There it transfers its positive charge to another metal comb connected to the large shell. Thus, positive charge is transferred to the shell, where it spreads out uniformly on the outer surface. An iron source placed inside the shell is at a high potential relative to ground. Therefore, charged particles can be accelerated to high energies along a tube to collide with a target for various experiments. Did you know? Because of the ability of the capacitor to block current flow, it is often used as a filter. An interesting demonstration with the Van de Graaff is to make someone's hair stand on the end. Dielectric mirror is composed of multiple thin layers of dielectric material, typically deposited on the substrate of glass or some other optical material. Summary. Let us summarize what we have learned. Polar materials are composed of molecules that have permanent electric dipole moments. Non-polar materials contain molecules that do not have permanent dipole moments. The extent to which the molecules of a dielectric become polarized by an electric field is described by a vector quantity called the electric polarization. Capacitor is a device that consists of two conductors isolated from each other so that they can be given equal but opposite charges. Capacitance is defined as the ratio of the magnitude of charge on either conductor to the magnitude of the potential difference between them. The dielectric constant of a dielectric is the factor by which the capacitance of a capacitor increases from its vacuum value when the dielectric fills the entire space between the plates of the capacitor. When a positively charged conductor is connected internally with a hollow conductor, the whole of its charge flows to the outer conductor.
तो मेरे प्यारे दोस्तों, ये था इलेक्ट्रिक पोटेंशियल एंड कैपेसिटेंस का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी कर्चहॉफ्स लॉ और व्हीटस्टोन ब्रिज जैसे सर्किट प्रॉब्लम्स में कंफ्यूजन होती है? क्या जब तुम रेजिस्टर्स और सेल्स को सीरीज और पैरेलल में देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त, इस वीडियो में हम इस चैप्टर के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और उस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इंपॉर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Today, Aarti and Rachna went to the market and then returned home. Aarti switched on the fan and the bulb. The fan was running at low speed, so Aarti rotated the regulator of the fan at its high speed. Rachna asked Aarti that how did the speed of the fan increase as you just rotated the regulator? How does it work? Aarti replied that the regulator of the fan works just like a variable resistor. At initial position, resistance was very high and the speed of the fan was low. But when I rotated the regulator, its resistance decreased to its minimum value and hence the speed of the fan maximized. It means that as the value of resistance decreases, the value of electric current increases. Students, today we will study more about the current electricity. Objectives. At the end of this lesson, you will be able to define electric current, understand electric current in conductors, define Ohm's law, calculate resistivity, know the limitations of Ohm's law, determine resistivity of various materials, evaluate temperature dependence of resistivity, define electrical energy and power, evaluate combination of resistors, understand cells and its combinations, state Kirchhoff's law, define Wheatstone bridge, meter bridge and potentiometer. Electric current. The electric current is defined as the time rate at which charge flows through a surface area. Let in time delta t, a net charge delta q flows through the area. The average electric current is given by delta q upon delta t. If the flow of charge is not steady, then the instantaneous electric current is given by dq upon dt. The SI unit of current is ampere. The current is in the direction opposite to the flow of electrons. The direction of electric current is taken to be in the direction of flow of positive charges. Electric current in conductors. For a current to flow in a conductor, a potential difference must exist across it. The current flows from high potential to low potential. When a battery is connected across the ends of a conductor, the surface charges of opposite sign build up on the conductor, starting from the two ends in contact with the battery terminals. These surface charges produce an electric field. This electric field causes electrons to move in a direction opposite to that of the field. Due to collisions, the electrons move slowly along the conductor and their average velocity is called the drift velocity Vd. This directed flow of electrons constitutes a current. Ohm's law. Ohm's law states that the potential difference applied across a conducting material is directly proportional to the current flowing through it. V is directly proportional to I, or V is equal to IR, where the proportionality constant R is called the resistance of the conducting material. The SI unit of resistance is ohm. Any electrical device offers a specified amount of resistance to the flow of current is called a resistor. We represent a resistor by this symbol. We consider a uniform electric field E exists along a wire of length L and cross-sectional area A. The potential difference across the ends of the wire is given by V is equal to EL, but I is equal to A upon rho L multiplied by V, where rho is equal to resistivity of the material. Put the value of I in the above equation. We get the value of resistance, which is equal to rho L upon A. We conclude that the resistance R of a wire is directly proportional to its length L and inversely proportional to its cross-sectional area A. Drift of electrons and origin of resistivity. When no electric field is applied, the random thermal velocities of the electrons produce no net current in any direction. When an electric field is applied, each electron experiences acceleration opposite to the field direction is given by A is equal to minus E, capital E, divided by M. Over a time interval delta t, the change in velocity of an electron due to the field E is equal to the product of acceleration and time interval. If tau is the average time between collisions, the average drift velocity of the electrons is equal to the product of acceleration and tau. The quantity tau is called the relaxation time. It is a measure of time for the system to relax back to thermal equilibrium through collision. Current density is given by J is equal to minus NEVD. Putting the value of Vd in the above equation, we get J is equal to NE square tau upon M multiplied by E. Hence, conductivity of the material is given by sigma is equal to NE square tau upon M. And resistivity of the material is given by rho is equal to M upon product of N, E square and tau. Mobility. The mobility of a mobile charge carrier in a conducting material is defined as the magnitude of the drift velocity per unit electric field. Mobility mu is equal to Vd upon E, which is equal to E tau upon m. Limitations of Ohm's law. Although Ohm's law has been found valid over a large class of materials, there do exist materials and devices used in electric circuits where the proportionality of V and I does not hold. The deviations are of the following types. The relation between V and I depends on the sign of V. On reversing the direction of V, keeping its magnitude fixed does not produce a current of the same magnitude as I in the opposite direction. V ceases to be proportional to I. There is more than one value of V for the same current I. A material exhibiting such behavior is gallium arsenide. Resistivity of various materials. Resistivity is an inherent property of a material. Conductors such as copper have small resistivity. Semiconductors are materials such as germanium with resistivity in a range of values intermediate to that of conductors and insulators. Insulators such as rubber have large resistivity. A color code scheme is used to indicate the resistance value of a resistor and its accuracy. A set of colored stripes are drawn around the resistor with their significance. Let's take an example. For the given resistor, yellow represents 4, violet represents 7, red represents 10 raised to the power 2, and gold represents 5%. On combining the above data, total resistance of the given resistor is 47 into 10 raised to the power 2 ohm with 5% tolerance. Temperature dependence of resistivity. The resistivity of a material depends on temperature. The relation between the temperature and resistivity is given by rho is equal to rho naught multiplied by 1 plus alpha T minus T naught, where rho and rho naught are the resistivity at temperatures T and T naught respectively. Alpha is called the temperature coefficient of resistivity. In metals, the resistivity increases with increasing temperature and alpha is positive. In alloys, the resistivity is very large but have weak temperature dependence. Alloy has residual resistivity even at absolute zero, while a pure metal has negligibly small resistivity at absolute zero. In semiconductors, the resistivity decreases with increasing temperature and alpha is negative. Electrical energy and power. Consider a portion of a circuit having current I and potential difference V between the two endpoints A and B. In a time interval delta t, an amount of charge delta q is equal to I delta t moves from a point A to B of the circuit, and the work done by the electric field is equal to product of V and delta q, which is equal to the product of V, I and delta t. The rate at which the electrical energy enters a portion of the circuit is called the electrical power input. P is equal to VI. The SI unit of power is the watt, W. Power dissipated in a resistor. When a potential difference V is maintained across a resistor, The free electrons in the resistor are accelerated by the electric field and gain kinetic energy. These electrons give up a part of their kinetic energy to the atoms in the resistor material when they collide with them. This transfer of energy to the resistor manifests itself as an increase in the temperature of the resistor. Power input to the resistor is given by P is equal to VI, which is equal to I square R, which is equal to V square divided by R. Combination of resistors. Two or more resistors may be connected to each other in certain combination to produce an equivalent resistance of any desired value. The equivalent resistance R of a combination of resistors is defined as the resistance of a single resistor which can replace the combination without changing the voltage across the combination and the current I in the rest of the circuit. There are two ways of combination of resistors: series combination and parallel combination. Resistors in series. Current through each resistor is the same current entering the combination. Potential drop across the series combination is equal to the sum of the potential drops across the individual resistors. For any number of resistance in series, R is equal to R1 plus R2 plus R3 plus and so on. The equivalent resistance is equal to the sum of the individual resistances. The equivalent resistance is always larger than the largest resistance in the series combination. Resistors in parallel. Potential drop across each resistor is the same. Total current entering the combination equals the sum of currents through the individual resistors. For any number of resistance in parallel, 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus and so on. The reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. The equivalent resistance is always less than the smallest resistance in the combination. Example. Let's take an example on combination of resistors. Calculate the resistance between A and B of the resistance network shown in the given figure. Let's see the solution. For calculating resistance RAB between A and B, we make an equivalent network shown in figure. Now we calculate resistance of arm GEFH, which is equal to 1 plus 1 plus 1 within parenthesis is equal to 3 ohm. This is in parallel with the resistance of arm GH. So, the effective resistance between G and H is equal to 0.75 ohm. Hence, the effective resistance between A and B is 2.75 ohm. Now, RAB is equal to 1 plus 0.75 plus 1 is equal to 2.75 ohm. Cells. The cell can maintain a potential difference across a resistor to give a steady flow of current in the resistor. As the current keeps on flowing, the positive charges keep on accumulating at the negative terminal of the cell. Unless these positive charges on negative terminal are constantly transferred to the positive terminal through the electrolyte inside the cell, the potential difference across the two terminals cannot be maintained constant. Work is required to be done for transferring the charges from one terminal to the other through electrolyte inside the cell, since the electrolyte medium offers resistance against the movement of charges. This is called the internal resistance of the cell. EMF. The work done per unit charge to force charge to move from lower to higher potential terminal inside the cell is called the electromotive force of the cell. EMF of the cell is given by E is equal to I within parenthesis capital R plus small r. Here capital R is the external resistance, small r is the internal resistance, small I is the current in circuit. An ideal cell has a zero internal resistance. The voltage applied to the circuit is equal to the EMF of the cell. Cells in series and parallel. Cells in series combination. In series, cells are joined end to end so that the same current flows through each cell. In ordinary series connection, the positive terminal of one cell is connected to the negative terminal of the second, the positive terminal of the second to the negative terminal of the third, and so on. When cells are connected in series, the EMF of the battery is equal to the sum of the EMFs of the individual cells. The total internal resistance is equal to the sum of the individual internal resistances of the cells. The current in each cell is the same and is equal to the current in the entire series combination. If n identical cells, each of EMF E and internal resistance R, are joined in series, the current in the circuit is equal to NE divided by R plus NR. Cells in parallel combination. Cells are said to be connected in parallel when the current is divided among the various cells. In ordinary parallel connection, all the positive terminals of the cells are connected together and all the negative terminals are connected together. When identical cells are connected in parallel, the EMF of the battery is equal to the EMF of a single cell. The reciprocal of the total internal resistance is equal to the sum of the reciprocals of the individual internal resistances of the cells. The current in the external circuit is divided equally among the cells. If n identical cells, each of EMF E and internal resistance R, are joined in parallel, the current in the circuit is equal to NE divided by NR plus R. Kirchhoff's laws. First law states that at any circuit junction, the sum of the currents entering the junction must equal the sum of currents leaving the junction. The algebraic sum of the currents entering or leaving a junction is 0. Summation of I is equal to 0. Second law states the sum of the potential changes across all the circuit elements found when traversing in one direction around any closed circuit loop must be 0. Summation of delta V is equal to 0. Wheatstone bridge. The Wheatstone bridge is a device that can be used for measuring an unknown resistance. It consists of a battery, a galvanometer, and a network of 4 resistors. Current I flows from the battery into junction A, where it divides into current I1 and I2. The galvanometer segment between junctions C and D forms the bridge. By adjusting the values of the resistances, the current in the galvanometer is made zero, as indicated by zero deflection. At this condition, the bridge is said to be balanced. The condition of the balanced bridge is R1 upon R2 is equal to R3 upon R4. A Wheatstone bridge is most sensitive when the resistances R1 and R2 are of the same order of magnitude. Meter bridge. A meter bridge is an application of Wheatstone bridge. The apparatus is essentially a slide wire bridge in which a uniform resistance wire of length exactly 1 meter is mounted on a wooden board between 2 fixed terminals A and C, along with a parallel meter scale which can measure any partial length of the wire. Across the whole wire length AC, we connect the cell. One end of the galvanometer is connected to the middle copper strip at point D, and its other end is connected to a jockey which can be connected to any required point on the wire. A resistance box is connected across the gap G1 and unknown resistance is connected across the gap G2. At the balance state, we have S is equal to product of R and within parenthesis 100 minus L upon L. To calculate the value of unknown resistance, we have to calculate only the balancing length accurately. Potentiometer. Potentiometer. Potentiometer is generally employed to compare the EMFs of 2 cells or any 2 sources of EMF. Potentiometer may also be used to determine the internal resistance of a cell, to measure current, to calibrate an ammeter or voltmeter, to compare resistances, and for the measurement of thermoelectric EMF. Principle of potentiometer. Potentiometer works on the principle that the potential difference across any length of a wire of uniform cross-section and uniform composition is proportional to its length when a constant current flows through it. The smaller the potential difference that can be measured with a potentiometer, more is the sensitivity of the potentiometer. The terminal A of the potentiometer is connected to its terminal B through a battery, an ammeter, a rheostat, and a one-way key. The positive terminal of the given cell, whose internal resistance is to be measured, is connected to the terminal A of the potentiometer, and negative terminal is connected to a slider S through a galvanometer G and a resistance box. The internal resistance of the cell is given by R is equal to L1 minus L2 upon L2 multiplied by R. Here, L1 is the balancing length when K2 is open. L2 is the balancing length when K1 is open. Did you know? George Simonov wanted to measure the motive force of electrical currents. He found that some conductors worked better than others and quantified the differences. He waited quite some time to announce Ohm's law because his theory was not accepted by his peers. The unit for resistance is named after him. Lightning is a discharge of electricity in the atmosphere. Lightning bolts can travel at around 210,000 kilometers per hour while reaching nearly 30,000 degrees Celsius in temperature. A resistor placed in a series with another component, such as that of a light-emitting diode, reduced the current to a known safer value. A battery explosion is caused by the misuse or malfunction of a battery, such as attempting to recharge a non-rechargeable battery or short-circuiting a battery. Car batteries are most likely to explode when short circuit generates very large currents. Summary. Let us summarize what we have learned. The electric current is defined as the time rate at which charge flows through a surface area. Due to collisions, the electrons move slowly along the conductor and their average velocity is called the drift velocity. Ohm's law states that the potential difference applied across a conducting material is directly proportional to the current flowing through it. The mobility of a mobile charge carrier in a conducting material is defined as the magnitude of the drift velocity per unit electric field. The equivalent resistance of a combination of resistors is defined as the resistance of a single resistor, which can replace the combination without changing the voltage across the combination and the current in the circuit. The work done per unit charge to force charge to move from lower to higher potential terminal inside the cell is called the electromotive force of the cell. Kirchhoff's first law states that at any circuit junction, the sum of the currents entering the junction must equal the sum of currents leaving the junction. Kirchhoff's second law states that the sum of the potential changes across all the circuit elements found when traversing in one direction around any closed circuit loop must be zero.
तो मेरे प्यारे दोस्तों, ये था करंट इलेक्ट्रिसिटी का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी मैग्नेटिक फोर्स और मैग्नेटिक फील्ड जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम बायट-सवार्थ लॉ और एम्पियर्स लॉ के फॉर्मूलास देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम इस चैप्टर के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है? तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और इस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इम्पोर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Today, our physics teacher is going to perform an experiment in the physics lab. She starts the experiment in front of the students. She took a cardboard having a hole at the center. She made an electronic circuit and passed the wire from that hole. Then, she sprinkles the iron dust on the cardboard uniformly. After set up the arrangement, she switches on the circuit. When she switches on, some movement is shown in the iron dust particles and they start arranging in concentric circles pattern. She performed this experiment to show you the magnetic effect of current. You saw the iron dust particles arranged into the concentric circle pattern due to the magnetic field generated by the electric current. Students, today we'll study more about the moving charges and magnetism. Objectives. At the end of this lesson, you will be able to explain Oersted's experiment, define Lorentz force, define Fleming's left hand and Maxwell's corkscrew rule, calculate magnetic force on a current-carrying conductor, explain motion in combined electric and magnetic fields, describe cyclotron, define Biot-Savart law, calculate magnetic field on the axis of a circular current loop. Oersted's experiment. Oersted observed that a straight wire carrying electric current deflected a nearby magnetic compass needle. When the wire is held above the needle and the current flows from south to north, the north pole of the magnetic needle gets deflected towards the west. And when the wire is placed below the needle, the direction of deflection of the needle is reversed. The alignment of the needle is tangential to a circle centered on the wire. The deflection is stronger on increasing the current or bringing the needle closer to the wire. Iron filings sprinkled around the wire arrange themselves in circles concentric to the wire. Aurora borealis. It is a natural phenomenon displayed as magnificent colors in the sky in the latitudes near the poles. Electrons and protons mostly emitted by the sun during a solar flare are trapped in helical paths along the Earth's magnetic field. These particles become crowded near the polar regions where the Earth's magnetic field lines are closer. They occasionally collide with atoms and molecules in the upper atmosphere, causing them to emit light. In the north, this phenomenon is called the aurora borealis, and in the south, it is called the aurora australis. Lorentz force. A charge q moving with a velocity v in a magnetic field B experiences a force generally known as the magnetic Lorentz force. It is given by F is equal to q into cross product of v and b. In magnitude, F is equal to qvb sin theta. The magnetic force on a charged particle moving in a magnetic field has its maximum value when the particle moves perpendicular to the magnetic field. F max is equal to qvb. minimum value when the particle moves in the direction of the magnetic field or opposite the field. F minimum is equal to 0. Fleming's left-hand rule. If the forefinger, central finger and thumb of left hand are stretched mutually perpendicular to each other, such that the forefinger may point field and central finger may point current, the thumb will show the direction of force. This rule is used for a current-carrying wire in a magnetic field, such as a wire on the armature of a motor. Maxwell's corkscrew rule. Imagine a right-handed corkscrew placed along the current-carrying conductor. If the screw is rotated so that it moves in the direction of flow of current, then the direction of rotation of the thumb gives the direction of magnetic lines of force. Magnetic force on a current-carrying conductor. The moving charge carriers constituting a current in a conductor experience magnetic force when the conductor is placed in a magnetic field. We consider a segment of a conductor of uniform cross-sectional area A carrying a current I in a uniform magnetic field B. We consider a current element I dl of the conductor. The number of free electrons in the element dl of the conductor is NaDl, where N is the number density of free electrons in the conductor. The magnetic force experienced by the current element IdL is given by minus ENaDl into cross product of V and B, which is equal to I into cross product of dl and B, where I is the current in the conductor. The resultant force F on the conductor is the vector sum of the contributions of all the elements constituting the conductor. Now we get the result F is equal to I into cross product of L and B. The magnitude of magnetic force on the straight conductor is given by F is equal to BIL sin theta. Example. Let's take an example of magnetic force on a current-carrying conductor. A horizontal wire 0.1 meters long carries a current of 6 ampere. What magnitude and direction of magnetic field can support the weight of this wire, where mass is 3 into 10 raised to the power minus 3 kilogram? Let's see the solution. Here, the given values are L is equal to 0.1 meters, I is equal to 6 amperes, M is equal to 3 into 10 raised to the power minus 3 kilogram. Force due to magnetic field on current carrying wire when the field is normal to the straight conductor is equal to BIL. Weight of wire is given by mg. On comparing these two equations we get BIL is equal to mg, which can be written as B is equal to mg divided by IL. By putting the values and calculating, we get the value of B is equal to 0.49 Tesla. Hence, magnetic field of 0.49 Tesla can support the weight of the wire. Circular motion in a magnetic field. We consider a charge Q traveling in a uniform magnetic field B with a velocity v perpendicular to B. As the magnetic force always acts perpendicular to v, the velocity of the charge changes only in direction, but the speed v remains constant inside the field. the force having a constant magnitude and its direction is always at right angles to V, gives rise to a uniform circular motion of the charge. The centripetal force required by the charge to describe a circular path is provided by the magnetic force. The radius of the circular orbit is given by mv divided by qb. Helical motion in a magnetic field. We consider the initial velocity v of the particle that makes an arbitrary angle with the field B. The velocity component parallel to the field remains constant, while the component perpendicular to the field results in a circular orbit. Radius of the helix is defined as the radius of the circular component of the orbit. Radius of helix is given by perpendicular component of velocity divided by frequency, which is equal to m into perpendicular component of velocity divided by qb. Motion in combined electric and magnetic fields. Velocity selector. If a charge with velocity enters a region where both electric field and magnetic field exist in such a way that the electric force and magnetic force are equal and opposite, then the charge will move undeflected in the fields. This can happen with velocity, electric field and magnetic field are mutually perpendicular to one another. Cyclotron. The cyclotron is a machine used for accelerating charged particles such as protons or ions to higher energies. Principle and working of cyclotron. Cyclotron works on the principle that a magnetic field can restrict a charged particle to move in a circular path with a frequency which is independent of its speed, whereas an electric field can accelerate it. The cyclotron consists of an evacuated chamber in which there are two Ds insulated from each other. The Ds are open along their straight edges. The chamber is placed between the poles of a very strong electromagnet. An electric oscillator establishes a high-frequency alternating voltage across the gap between the Ds. The source produces the ions to be accelerated. Suppose an ion with a positive charge Q and mass m is at the center of gap when D1 is at negative potential with respect to D2. The ion is accelerated across the gap by the electric field between the Ds towards D1. Inside a D, the magnetic field causes the ion to bend its path into a semicircle of radius r inside a D. Here, charge follow the given relation. QVB is equal to mv squared divided by r. The cyclotron frequency at which the ions circulate in the field is given by QB divided by 2 pi m. And time taken by the ion to complete a semicircle in a D is given by pi m divided by QB. At resonance condition, the ion arrives between the Ds exactly in time to be repeatedly accelerated and gains energy. This energy gain does not affect the resonance condition except increasing the orbit size. The ion describes a spiral path, gaining energy each time it passes the gap, but remaining in phase with the alternating voltage. The ion acquires the required energy to have a radius approximately that of the Ds. It is then deflected by a negatively charged plate and leaves the system. The maximum energy attained by the ion is given by product of B square, R square and Q square divided by 2m. Applications and limitations of cyclotron. It is used in the study of nuclear reactions. It is used to implant ions into solids and modify their properties. It is used to produce radioactive substances which can be used in diagnosis and treatment of ailments. At high speeds, the cyclotron frequency decreases due to realistic mass increase, causing the particles to get out of resonance with the electric oscillator. It can be used for accelerating electrically neutral particles such as neutrons. Biot-Savart law. It is a mathematical description of the magnetic field at a point that arises from a current flowing through a current element. Biot-Savart law states that the magnitude of the magnetic field dB at any point P, located at position vector r, with respect to the current element IdL carrying a current I is proportional to the current I, proportional to the length dl of the current element, proportional to sin theta, where theta is the angle between r and dl, and inversely proportional to the square of the distance r of the point P from the current element. Mathematical form of Biot-Savart law. In mathematical form, dB is equal to K multiplied by I and cross product of dl and r cap divided by r square, where K is the proportionality constant and its value is given by mu naught upon 4 pi. Now Biot-Savart law becomes in vector form is given by dB is equal to mu naught upon 4 pi multiplied by I and cross product of dl and r cap divided by r square. And in magnitude form, dB is equal to mu naught upon 4 pi multiplied by I dl sin theta divided by r square. Magnetic field on the axis of a circular current loop. Consider a circular loop of radius r through which current I is flowing. We have to calculate the magnetic field at a point P due to this current loop. The point P lies on the axis of the circular current loop. We consider an infinitesimally small element AB of length dl. According to Biot-Savart law, the magnetic field at P is given by mu naught upon 4 pi multiplied by I dl sin theta divided by a square. Here, theta is equal to 90 degrees and sin theta is equal to 1. Therefore, the magnetic field at P is given by mu naught upon 4 pi multiplied by I dl divided by a square. The magnetic fields at P due to different elements will be in different directions. All the components parallel to CP get added up, while those perpendicular to CP cancel out. Now the total magnetic field at P due to the whole of the current loop is given by closed integral of dB sin beta. By putting the values in this equation, we get a total magnetic field at P is equal to mu naught I upon 4 pi a square multiplied by sin beta and 2 pi r. But sin beta is equal to r upon a. Therefore, total magnetic field at P is equal to mu naught I r square divided by 2a cube. We can also write this equation as mu naught I r square divided by 2 r square plus x square within parenthesis raised to the power 3 by 2. This magnetic field acts along the axis of the circular coil. Did you know? The cyclotrons and their beam lines consume about 1.5 megawatts of power. All known magnetic fields have been found to be produced either by electric currents or by atomic magnetic moments or by time-dependent electric fields. The low-resistance shunt serves the dual purpose of increasing the range of the meter and reducing its net resistance very substantially. Summary. Let us summarize what we have learned. Oersted observed that a straight wire carrying electric current deflected a nearby magnetic compass needle. The magnetic force on a charged particle moving in a magnetic field has its maximum value when the particle moves perpendicular to the magnetic field. Fleming's left-hand rule is used for a current-carrying wire in a magnetic field, such as a wire on the armature of a motor. Maxwell's corkscrew rule states, if a screw is rotated so that it moves in the direction of flow of current, then the direction of rotation of the thumb gives the direction of magnetic lines of force. The centripetal force required by the charge to describe a circular path is provided by the magnetic force. Radius of the helix is defined as the radius of the circular component of the orbit. The cyclotron is a machine used for accelerating charged particles such as protons or ions to high energies. A magnetic field can restrict a charged particle to move in a circular path with a frequency which is independent of its speed, whereas an electric field can accelerate. Introduction. Today, Ravi is alone at home. He is doing his study. Suddenly, the doorbell rings. He opens the door and greets with a smile on seeing his father. Ravi asked his father how the doorbell works. His father replied to him that the doorbell works on the principle of solenoid. Solenoid is a circular current-carrying coil. When the current passes through it, then it behaves like a magnet. Students, you also must be curious like Ravi to know more about this. So today, we'll explore the moving charges and magnetism. Objectives. At the end of this lesson, we'll be able to define Ampere's circuital law, describe solenoid and toroid, evaluate force between two parallel current-carrying conductors, calculate torque on a rectangular current loop, calculate magnetic dipole moment of a revolving electron, explain moving coil galvanometer, convert galvanometer into ammeter and voltmeter. Ampere's circuital law. Ampere's circuital law relates the integrated magnetic field around a closed loop to the electric current passing through the loop. It states that the line integral of the magnetic field B along any closed path is equal to mu naught times the net current I passing through the area bounded by the path. It is mathematically represented by close integral of B dot dl is equal to mu naught I. It provides a simple method for calculating the magnetic fields of current configurations which has high symmetry. Magnetic field due to an infinitely long current carrying wire. We have to calculate the magnetic field at a distance r from the wire. By symmetry, the magnitude of the field B is the same at all points of the loop and its direction at a point is along the tangent to the circle at the point. The line integral of the magnetic field B around the circular loop is given by product B and 2 pi r. Also, by Ampere's circuital law, closed integral of B dot dl is equal to mu naught I. From above two equations, we get the result B is equal to mu naught I divided by 2 pi r. Example. Let's take an example on magnetic field due to a current-carrying conductor. A long straight conductor carries a current of 120 ampere. At what distance from the conductor is the magnetic field caused by the current equal to 0.8 into 10 raised to the power minus 4 Tesla? Let's see the solution. Here, the given values are I is equal to 120 ampere, B is equal to 0.8 into 10 raised to the power minus 4 Tesla, mu naught is equal to 4 pi into 10 raised to the power minus 7 SI units. We know that B is equal to mu naught I upon 2 pi A. By putting the values in the equation, we get the values of A is equal to 0.3 meters. Hence, at 0.3 meters from the conductor, the magnetic field caused by the current equal to 0.8 into 10 raised to the power minus 4 Tesla. Solenoid. A solenoid is a current-carrying wire wound around the surface of a right circular cylinder. To find the magnetic field inside a long solenoid, we consider a rectangular loop ABCD. The segment AB of length L is parallel to the axis of the solenoid. The integral for the rectangular path ABCD consists of 4 integrals, one for each segment. Closed integral of B dot dl is equal to integration from A to B of B dot dl plus integration from B to C of B dot dl plus integration from C to D of B dot dl plus integration from D to A of B dot dl. It gives closed integral of B dot dl is equal to integration from A to B of B dot dl, which is equal to BL. According to Ampere's circuit law, closed integral of B dot dl is equal to mu naught NIL, where N is the number of turns per unit length. From above two equations, we get the result B is equal to mu naught Ni. Toroid. A toroid is a current-carrying wire wound around a donut-shaped core. An ideal toroid consists of closely spaced current turns that the magnetic field is completely confined to the interior of the donut. From symmetry, the magnitude of the magnetic field B is the same at all points on the circle of radius r and is directed tangentially to the circle at any point. Thus, the line integral of the magnetic field B around the circular loop is given by the product of B and 2 pi r. According to Ampere's circuit law, closed integral of B dot dl is equal to mu naught Ni, where N is the total number of turns. From above two equations, we get the result B is equal to mu naught Ni divided by 2 pi r. Field due to parallel currents. It represents the combined magnetic field due to two parallel conductors carrying current in the same direction. The pattern of the magnetic field indicates attraction between the conductors. It represents the combined magnetic field due to two parallel conductors carrying currents in opposite direction. The pattern of the magnetic field indicates repulsion between conductors. Force between two parallel current-carrying conductors. Let us consider two long, straight, parallel wires separated by distance r and carrying currents I1 and I2 in opposite directions. Wire 1 carries a current I1, sets up a magnetic field B1 at all points along the wire 2. This magnetic field is directed perpendicularly upward to wire 2 and has the magnitude equal to mu naught I1 divided by 2 pi r. The magnetic force magnitude on wire 2 due to wire 1 is given by mu naught I1 I2 L divided by 2 pi r. An equal and opposite force, F12, acts on wire 1 due to the magnetic field produced by wire 2. F21 is equal to minus F12. Consequently, the forces between the wires are repulsive. In case the currents are in the same direction in the two wires, the forces between the wires are reversed and hence attractive. One ampere. We know that F is equal to mu naught upon 2 pi multiplied by I1 I2 upon R, when I1 is equal to I2 is equal to 1 ampere and R is equal to 1 meter. Then the value of F is equal to 2 into 10 raised to the power minus 7 Newton per meter. Therefore, 1 ampere is that current which, if passed in each of the two parallel conductors of infinite length and 1 meter apart in vacuum, causes each conductor to experience a force of 2 into 10 raised to the power minus 7 Newton per meter of length of conductor. Torque on a rectangular current loop. We consider a current carrying rectangular loop PQRS of sides A and B placed in an external uniform magnetic field B. The normal to the plane of the loop makes an angle theta with B. When a current I flows through the loop, each straight segment experiences a force. The forces F1 and F3 are equal in magnitude, opposite in direction and collinear, so the net force and torque due to these forces are zero. The forces F2 and F4 are also equal in magnitude and opposite in direction, so they produce no net force. However, since the two forces are not collinear, they exert a torque on the loop, with magnitude equal to product of force and lever arm, which is equal to IAB sin theta, where A is the area of loop. The above equation can be written as tau is equal to mb sin theta, where m is the magnitude of magnetic dipole moment. Tau is equal to the cross product of m and b. Current loop as a magnetic dipole. The magnetic dipole moment m of a circular current loop carrying a current I and of area A is given by m is equal to product of I and A r cap. The direction of m is given by the right-hand thumb rule. Right-hand thumb rule states that if the current is directed along the four curved fingers of the right hand, then the extended thumb points in the direction of the magnetic dipole moment. Magnetic dipole moment of a revolving electron. The magnetic moment arising from the orbital motion of the electron is given by EVR by 2. The direction of this magnetic moment is perpendicularly into the plane. If ME is the mass of the electron, the revolving electron also possesses an angular momentum with magnitude. I is equal to MEVR. From above two equations, we get the result mu L is equal to minus E upon 2 ME multiplied by L. The negative sign indicates that the two vectors are in opposite directions. Gyromagnetic ratio. Mu L upon L is equal to E upon 2 ME. Its value is 8.8 into 10 raised to the power 10 coulomb per kilogram for an electron. Bohr magneton. Mu B is equal to EH upon 4 pi ME. Its value constant and equals to 9.27 into 10 raised to the power minus 24 atm square. Moving coil galvanometer. The galvanometer is a device used in the construction of both ammeter and voltmeter. It works on the principle that a current-carrying coil suspended in a uniform magnetic field experiences a torque which balances the restoring torque produced by the twisting of the suspension spring. The galvanometer consists of a coil of fine wire of many turns wound on a cylindrical soft iron core hung from a spring and carrying the current I to be measured. The pole pieces are cylindrical in shape so that the coil rotates in a field that is everywhere radial. This radial force ensures that the deflecting torque is directly proportional to the current and is always constant. Parameters of moving coil galvanometer. The steady deflection for a galvanometer is given by NBA upon K multiplied by I, where N is number of turns in the coil, A is the area of coil, and K is the torsional constant of the spring. The current sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit current flows through it. Current sensitivity is equal to phi upon I, which is equal to NBA upon K. The voltage sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit voltage is applied across it. Voltage sensitivity is equal to phi upon V, which is equal to NBAI upon KV. Conversion of galvanometer into ammeter. To measure the current in a circuit, an ammeter must be inserted in series in the circuit so that the current to be measured passes through it. The range of the galvanometer can be extended, and at the same time, the equivalent resistance can be reduced by connecting a low resistor S in parallel with the galvanometer. The resistor S is called the shunt resistor. The galvanometer and parallel resistor combination is called an ammeter. V is equal to product of Ig and G, or V is equal to product of Is and S. On equating both above equations, we get the value of S is equal to Ig upon Is into G. We know that I is equal to Ig plus Is. Hence, the value of S is equal to Ig upon I minus Ig into G. With this value of S, the ammeter is able to measure a large current up to I, and it has a low resistance. Conversion of galvanometer into voltmeter. To measure potential difference across a given section of a circuit, the voltmeter must be connected in parallel with that section of the circuit. The range can be extended, and at the same time, the equivalent resistance can be increased by connecting a resistance in series with the galvanometer. The galvanometer and series resistor combination is called a voltmeter. Applying Ohm's law to the circuit, we get V upon Rs plus G within parentheses is equal to Ig. It can be written as Rs is equal to V upon Ig minus G. Rs must be put in series with the galvanometer in order that it may be used as a voltmeter. The voltmeter has a high resistance Rs plus G within parentheses. Did you know? A solenoid switch is used as a control device. It utilizes electromagnetic energy so as to convert the input electrical energy to mechanical energy. Modern uses for the galvanometer mechanism are in positioning and control systems. Solenoid is used as an interlock device for integration into automatic gearbox drive selectors, petrol cap locking, vibration engine mountings and security systems. Summary. Let us summarize what we have learnt. Ampere's circuit law relates the integrated magnetic field around a closed loop to the electric current passing through the loop. A solenoid is a current-carrying wire wound around the surface of a right circular cylinder. A toroid is a current-carrying wire wound around a donut-shaped core. When the currents are in the same direction in the two conducting wires, the forces between the wires are attractive. 1 ampere is that current which, if passed in each of the two parallel conductors of infinite length and 1 meter apart in vacuum, cause each conductor to experience a force of 2 into 10 raised to the power minus 7 Newton per meter of length of conductor. Right-hand thumb rule states that if the current is directed along the 4 curved fingers of the right hand, then the extended thumb points in the direction of the magnetic dipole moment. Moving coil galvanometer works on the principle that a current-carrying coil suspended in a uniform magnetic field experiences a torque which balances the restoring torque produced by the twisting of the suspension spring. The current sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit current flows through it. The galvanometer and series resistor combination is called a voltmeter.
तो मेरे प्यारे दोस्तों, ये था मूविंग चार्जेस एंड मैग्नेटिज्म का एक कॉम्प्रिहेंसिव लेक्चर. हमने हर कॉन्सेप्ट को जीरो से समझा है. एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे. उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है. दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है. इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है. तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं. चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो. ऑल द बेस्ट. हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर. क्या तुम्हें भी डायमैग्नेटिज्म और फेरोमैग्नेटिज्म जैसे टर्म्स में कंफ्यूजन होती है? क्या जब तुम अर्थ्स मैग्नेटिज्म के एंजल्स जैसे एंगल ऑफ डिप देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त. इस वीडियो में हम इस चैप्टर के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे. लेकिन उससे पहले एक जरूरी बात. हमारे चैनल पर 97% लॉग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं. यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं. इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है. तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और इस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इंपॉर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके. ओके.
Introduction. Aman, can you please come here? I want to ask you something. What happened today? See there. Machine is moving the scrap of iron and steel from the waste material. Yes, I can see that. But how is it possible to extract the desired material from the wastage? It is simple. Basically, it is an electromagnetic crane which works on the principle of magnetism. Its anchor is made up of an electromagnet. When electric current is passed through it, it behaves like a magnet and attracts only iron and steel from the scrap. Okay, I got the answer of my question, and I want to know more about this. Will you please tell me? Sure. Today we will study about the magnetism and matter. Objectives. At the end of this lesson, you'll be able to define magnetism and bar magnet, know about magnetic field lines, analyze bar magnet as an equivalent solenoid, analyze dipole in a uniform magnetic field, describe Gauss's law in magnetism, know about Earth's magnetism, define magnetization and magnetic intensity, understand magnetic properties of material, analyze hysteresis curve, describe permanent magnets and electromagnet. Definition. The phenomenon of attracting magnetic substances like iron, nickel, cobalt, etc. is called magnetism. A body possessing the property of magnetism is called magnet. The two centers of attraction in any magnet are called its poles and are named as North Pole and South Pole. The region around a magnet in which it exerts forces on other magnets and on objects made of iron is called a magnetic field. Bar magnet. A magnet in the form of a bar with magnetic poles at each end is known as a bar magnet. The main properties of a bar magnet are as follows. When a magnet is suspended freely, it aligns itself with one end pointing towards north of Earth and other towards south of Earth. Unlike poles attract and like poles repel each other. A magnet attracts magnetic materials. This attraction is maximum at the poles. Isolated magnetic pole does not exist. Magnetic poles always exist in pairs. A magnet can induce magnetism in substances like soft iron, cobalt, nickel, and various ferrous alloys. Magnetic field lines. A magnetic field can be represented by lines called the magnetic field lines. A magnetic field line is defined as the curve, the tangent to which at any point gives the direction of the magnetic field at that point. Magnetic field lines never intersect each other. The magnetic field is stronger in regions where the field lines are relatively close together and weaker where they are relatively far apart. Magnetic field lines are always closed continuous loops. Bar magnet as an equivalent solenoid. The magnetic field patterns are similar of solenoid and bar magnet. Also, the solenoid itself behaves as a bar magnet with the north pole on one side and the south pole on the other side. Two adjacent solenoids can be either attracted to or repelled from each other, depending on the relative directions of the currents. Let us consider a solenoid of length 2L and radius r composed of a series of n current loops, each carrying a current I. The magnitude of magnetic field at an axial point P due to this elemental loop is given by mu naught upon 4 pi multiplied by 2m upon r cube, when m is the magnetic moment of solenoid. This is exactly the same as that of a bar magnet at far off axial point. Dipole in an uniform magnetic field. We consider a bar magnet of pole strength Qm and length 2L placed at an angle theta with a uniform magnetic field B. The forces exerted by magnetic field on the two poles are equal and opposite so that they form a couple. Torque is equal to force into lever arm. By putting the values in the above equation, we get the value of torque equals to mb sine theta. Vectorially, it is represented as tau is equal to cross product of m and b. This is exactly the same as that of a current carrying coil in a magnetic field. Potential energy of the magnetic dipole with dipole moment m in the field B is given by negative dot product of m and b. Example. Let's take an example of dipole in a uniform magnetic field. A short bar magnet of magnetic moment 0.40 joule per Tesla is placed with its axis at an angle of 30 degree with a uniform external magnetic field of 0.16 Tesla. Find the magnitude of the torque exerted on the magnet by the field. Let's see the solution. Here given values are m is equal to 0.40 joule per Tesla, theta is equal to 30 degree, b is equal to 0.16 Tesla. We know that tau is equal to cross product of m and b, or in terms of magnitude, tau is equal to mb sine theta. Put the values in the above equation. Tau is equal to 0.40 into 0.16 into sine 30 degree. On calculating the equation, we get the value of tau, which is equal to 0.032 joules. Hence, torque exerted on the magnet by the field is equal to 0.032 joules. Gauss's law in magnetism. Magnetic flux. It is a measure of the number of magnetic field lines cutting through a hypothetical surface in a magnetic field. If a loop of wire enclosing a planar area A is placed in a uniform magnetic field B, then the magnetic flux phi B through the loop is given by dot product of B and A, which is equal to BA cos theta, where theta is the angle between magnetic field and the normal to the plane of the loop. For an arbitrary closed surface immersed in a general magnetic field, the magnetic flux is defined as an integral over the surface. Phi B is equal to closed integral of B dot dA. Gauss's law of magnetism states that the net magnetic flux through a closed surface is always zero. Closed integral of B dot dA is equal to 0. The SI unit of magnetic flux is Weber. Earth's magnetism. The magnetic field at the surface of the Earth varies from 0.3 G to 0.6 G. The straight line passing through the magnetic north and south poles of the Earth is called its magnetic axis. The geographic and magnetic axes of the Earth are inclined at an angle of about 11.3 degree. The possible source of the Earth's magnetic field is charge-carrying convection current in the outer, liquid part of the Earth's core. This phenomenon is known as dynamo effect. The magnetic meridian at a place is the vertical plane passing through the place and the magnetic axis. The great circle on the Earth's surface perpendicular to the magnetic axis is the magnetic equator. Declination, alpha. The angle between the geographical meridian and magnetic meridian at a place is called the magnetic declination at that place. Angle of dip, delta. The angle between the Earth's magnetic field and the horizontal direction at a place is called the angle of dip at that place. The angle of dip is 0 at the magnetic equator and 90 degree at the magnetic poles. Horizontal component of Earth's magnetic field, BH. It is the component of the Earth's magnetic field in the horizontal direction. Tan delta is equal to BV divided by BH. We can also write this equation as B is equal to under root of BH square plus BV square. Magnetization and magnetic intensity. The magnetic state of a bulk piece of material is characterized by its magnetization, which is defined as the magnetic dipole moment per unit volume. The magnetization depends on both the magnitude of the individual atomic dipole moments and their degree of alignment. Magnetic field intensity. It is defined as the ratio of the magnetic field in free space to the permeability of the free space. H is equal to B naught divided by mu naught. The magnetic intensity depends on the geometry of the circuit and the conduction current, but not on the medium. The total magnetic field in a magnetic material is due to the conduction current in the external circuit and the microscopic current developed in the material. B is equal to B naught plus mu naught M. It can also be written as B is equal to mu naught multiplied by H plus M. The magnetic field is also called the magnetic flux density or the magnetic induction. The magnetic susceptibility of a material is defined as the ratio of M to H. It is a measure of how susceptible a material is to being magnetized when placed in an external field of intensity H. M is equal to product of Xi and H. Magnetic properties of material. Materials can be divided broadly into the following three categories: diamagnetic substances, paramagnetic substances, ferromagnetic substances. Diamagnetic substances. Diamagnetic substances are those which are feebly repelled by magnets and tend to move from high to low magnetic field region. The individual atoms do not possess any net magnetic moment on their own. The magnetization M varies with H in a linear way. M is equal to Xi H. The magnetic susceptibility is a small negative number and is independent of temperature. The relative permeability is slightly less than 1. The superconductors exhibit perfect diamagnetism. The phenomenon of perfect diamagnetism in superconductors is called the Meissner effect. Paramagnetic substances. Paramagnetic substances are those which are feebly attracted by magnets and tend to move from low to high magnetic field region. The individual atoms possess permanent magnetic dipole moment. The susceptibility is a small positive number and it is inversely proportional to the absolute temperature. Xi is equal to C upon T. The relative permeability is slightly greater than 1. Ferromagnetic substances. Ferromagnetic substances are those which are strongly attracted by magnets and tend to move from high to low magnetic field region. Atoms have permanent magnetic dipole moments which are spontaneously organized into domains of uniform magnetization. M is not directly proportional to H. The susceptibility is positive and very large, but no longer constant. Xi is equal to C upon T minus Tc. The relative permeability is much greater than 1. Two effects may occur when a ferromagnetic material is placed in an external magnetic field: rotation of the domains so that they become more closely aligned with external field, increase in the size of those domains that are already aligned with the field. Hysteresis curve. We consider a ferromagnetic material inserted in a solenoid. Initially, both H and B are 0. We increase H by increasing the current. The magnetization and hence B increases to its saturated value as shown by the segment AB. We now decrease H to 0. B does not retrace its original path but follows the path BC. The value of B at point C when H is equal to 0 is called retentivity. If we reverse the current, we reach the point D at which B is equal to 0. The value of H at point D when B is equal to 0 is called coercivity. As we further increase the reversed current, B saturates in the opposite direction at point E and turning the current to 0 at point F. If B increase the current, B again gets saturated value at point B. The path BCDEFGB can be repeatedly followed. The closed curve BCGEFGB, which represents a cycle of magnetization of a ferromagnetic material, is called its hysteresis loop. Hard ferromagnetic materials have large coercivity and are characterized by broad hysteresis loop. These materials are used to make permanent magnets. Soft ferromagnetic materials have small coercivity and are characterized by narrow hysteresis loop. They dissipate less energy when they are cycled through a hysteresis loop. They are used in devices such as transformers. Permanent magnets and electromagnet. Materials which retain their ferromagnetic property for a long period of time are called permanent magnets. For making permanent magnets, materials are selected which have high retentivity so that the magnet is strong and high coercivity. For example, steel, alnico, and cobalt steel. Solenoids are often referred to as electromagnets. Frequently, ferromagnetic materials, which have high permeability and low retentivity, are placed inside a solenoid to make strong electromagnets. Electromagnets are used in electric bells, loudspeakers, telephone diagrams, magnetic resonance imaging, MRI, cranes to lift heavy materials. Electromagnets have several advantages over permanent magnets. The north and south poles of an electromagnet can be readily switched by reversing the current. The strength of the magnetic field can be altered by changing the current or the number of turns per unit length. Did you know the Earth's magnetic field is not constant in time? It has been found that the direction of the Earth's magnetic field has been reversed several times during the last million years. Magnets can be used to decrease the white cell blood count, which increases in most diseases. Birds are able to find their way home by using the Earth's magnetic field to guide them on long-distance flights. Summary. Let us summarize what we have learned. The region around a magnet in which it exerts force on other magnets and on objects made of iron is called a magnetic field. A magnet is in the form of a bar with magnetic poles at each end is known as bar magnet. A magnetic field line is defined as the curve, the tangent to which at any point gives the direction of the magnetic field at that point. Gauss's law for magnetism states that the net magnetic flux through a closed surface is always zero. The possible source of the Earth's magnetic field is charge-carrying convection current in the outer, liquid part of the Earth's core and is known as dynamo effect. The magnetization depends on both the magnitude of the individual atomic dipole moments and their degree of alignment. Magnetic field is defined as the ratio of the magnetic field in free surface to the permeability of the free surface. The angle between the geographical meridian and magnetic meridian at a place is called the magnetic declination at that place. The closed curve, which represents a cycle of magnetization of a ferromagnetic material, is called its hysteresis loop.
तो मेरे प्यारे दोस्तों, ये था मैग्नेटिज्म एंड मैटर का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी मैग्नेटिक फ्लक्स और फैराडेस लॉ जैसे कॉन्सेप्ट्स में कंफ्यूजन होती है? क्या जब तुम लेंस लॉ और मोशनल ईएमएफ के फॉर्मूलास देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम इस चैप्टर के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात। हमारे चैनल पर 97% लॉग वीडियोस देखते हैं, लेकिन सब्सक्राइब नहीं करते। और सिर्फ 0.6% लॉग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और इस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इंपॉर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. It's evening. Dev and Mohan returned home after shopping. Mohan switches on the fan and bulb. As he saw that two bulbs are on, he switches off one bulb. Dev was watching this carefully and thinking of something. Then Dev said to Mohan that when you switch on the bulb, it doesn't glow instantly. And also, when you switch off the bulb, it doesn't diminish instantly. What is the reason behind that? Mohan told him that it is due to the induction of current. The induced current always tries to oppose the course of change. When bulb turns on, then an induced current develops such that it tries to remain off. Similarly, when bulb turns off, then an induced current develops such that it tries to remain on. That's why the bulb doesn't glow and diminish instantly. Students, electromagnetic induction is everywhere around us. We use many appliances or applications that are based on it. So today we'll study about the electromagnetic induction. Objectives. At the end of this lesson you'll be able to define electromagnetic induction, understand the experiments of Faraday and Henry, define magnetic flux, understand Faraday's law of induction, state Lenz's law and conservation of energy, define motional electromotive force and energy consideration, define eddy currents, calculate mutual inductance and self-inductance, describe AC generator. Definition. In our everyday life, electromagnetic induction plays a vital role. Transformer, generator, train, and telephone are some examples which work on the principle of electromagnetic induction. An electric current can be produced in a circuit by a changing magnetic field. The current in the coil brought about by a changing magnetic field is called an induced current and is said to be set up by an induced EMF in the coil. The phenomenon of producing an induced EMF with the help of a magnetic field is called electromagnetic induction. The experiments of Faraday and Henry. Experiment 1. Consider a bar magnet that can slide back and forth along the axis of a helical coil of wire to which a galvanometer is connected. When the magnet is at rest, no current is observed in the coil. The magnetic field at the coil is not changing. When the magnet moves towards the coil, a current flows in the coil. As the magnet approaches, the magnetic field produced by it at the location of the coil increases. When the magnet moves away from the coil, a current is again produced, but in the opposite direction. The magnetic field at the coil decreases. We conclude that only relative motion between the magnet and the coil is required to produce the current. Experiment 2. Consider two coaxial coils, one called the primary coil P connected to a battery via a key K, and the other called the secondary coil S connected to a galvanometer. When the key is closed, the galvanometer in the secondary circuit deflects momentarily and then returns to zero. The magnetic field at the secondary coil increases from 0 to a steady value. When the key is opened, the galvanometer deflects momentarily in the opposite direction and again returns to 0. The magnetic field at secondary coil decreases from the steady value to 0. The galvanometer reaches 0 when there is a steady current in P. Here the magnetic field at the secondary coil is not changing. Magnetic flux. It is a measure of the quantity of magnetism, being the total number of magnetic lines of force passing through a specified area in a magnetic field. If a uniform magnetic field B acts perpendicular to the plane surface, then the magnetic flux through the area A is given by the product of B and A. If the magnetic field B makes an angle theta with the normal to the surface, then the magnetic flux is given by BA cos theta. Or it can be written as phi is equal to dot product of B and A. Magnetic flux linked with a closed surface may be defined as the product of the surface area and the normal component of the magnetic field acting on that area. Faraday's law of induction. Faraday summarized the results of his experiments in the following two laws. Whenever the magnetic flux through a circuit changes, an EMF is induced in the circuit and it lasts only as long as the change in flux is taking place. The instantaneous EMF induced in a circuit is equal to the time rate of change of magnetic flux through a surface enclosed by that circuit. E is equal to minus differentiation of phi B with respect to t. The negative sign is introduced to indicate the direction of the induced EMF. The induced EMF always in the opposite direction of change in magnetic flux. If a coil of wire consists of n loops, each with the same area, then the flux through all loops is given by minus n differentiation of phi B with respect to t. Example. Let's take an example on Faraday's laws of induction. The magnetic flux through a coil perpendicular to its plane and directed into the paper is changing according to the relation. Phi is equal to 5t square plus 10t plus 3 meter Weber. Calculate the EMF induced in the loop at t which is equal to 5 seconds. Let's see the solution. Given phi is equal to 5t square plus 10t plus 3 meter Weber, it can be written as phi is equal to 5t square and 10t plus 3 multiplied by 10 raised to the power minus 3 Weber. We know that E is equal to d phi by dt. By putting the values in this equation we get E is equal to 3 plus 1 multiplied by 10 raised to the power minus 2 volt. Now substituting the value of t as 5 seconds, we get E as 0.06 volt. Hence the EMF induced in the loop at t is equal to 5 seconds is 0.06 volt. Lenz's law and conservation of energy. Lenz's law states that the direction of the induced EMF or induced current is such that it opposes the change that is producing it. When the magnet is pushed towards the coil, the induced current produced will oppose the push of the magnet by creating a north pole on the face of the coil near the magnet. When the magnet is pulled away from the coil, the induced current produced will oppose the pull of the magnet by creating a south pole on the face of the coil near the magnet. According to Lenz's law, the induced EMF opposes the change that produces it. We perform mechanical work in causing the change in magnetic flux. So, it is the mechanical energy which is converted into electrical energy. Thus, Lenz's law is in accordance with the law of conservation of energy. Motional electromotive force. Let us consider a straight conductor moving in a uniform and time-independent magnetic field. Let a rectangular conductor PQRS, in which the conductor PQ is free to move. The rod PQ is moved with a constant velocity v. It is placed in a uniform magnetic field B, which is perpendicular to the plane of the system. If the length RQ is x and RS is L, the magnetic flux phi B enclosed by the loop PQRS is equal to BLX, but x is changing with time. So the rate of change of flux will induce an EMF given by minus differentiation of BLX with respect to time, which is equal to BLV. The induced EMF BLV is called motional EMF. So we can produce induced EMF by moving a conductor inside uniform magnetic field. Energy consideration. Let R be the resistance of movable arm PQ of the rectangular conductor. The overall resistance of the rectangular loop is R, and this does not change as PQ is moved. The current I in the loop is given by E divided by R, which is equal to BLV divided by R. The force exerted on the arm PQ due to magnetic field is given by ILB, which is equal to the product of B square, L square and V divided by R. Power required to push the arm PQ with a constant speed V is given by product of B square, L square and V square divided by R. Thus, mechanical energy which was needed to move the arm PQ is converted into electrical energy and then to thermal energy. Eddy currents. Eddy current is defined as currents induced in a thick conductor when the conductor is placed in a changing magnetic field. Consider a conductor placed in a continuously changing magnetic field. Due to the continuous change of magnetic flux linked with the conductor, induced currents will be set up in the body of the conductor itself. These currents assume a circular path and their direction is given by Lenz's law. Eddy currents are used to advantage in certain applications like electromagnetic damping, induction furnace, magnetic braking in trains, electric power meters. Mutual inductance. The phenomenon in which a changing current in one circuit induces an EMF in another circuit is called mutual induction. Let us consider two long coaxial solenoids, each of length L. The inner solenoid S1 is of radius R1 with N1 turns per unit length, while the outer solenoid S2 has radius R2 with N2 turns per unit length. B1 is equal to product of mu naught, N1 and I1. The magnetic flux through a single turn of S2 is given by mu naught N1 pi R1 square I1. The magnetic flux linkage is solenoid S2 having a total number of N2L turns is given by mu naught N1 N2L pi R1 square I1. M21 of circuit 2 with respect to circuit 1 is given by mu naught N1 N2 L pi R1 square. Similarly, we calculate the value of M12 and is given by mu naught N1 N2 L pi R1 square. From above two equations, we can say that M12 is equal to M21, which equals M. And the value of M is given by mu naught N1 N2 L pi R1 square. Self-inductance. The phenomenon in which a changing current in a circuit induces an EMF in the same circuit is called as self-induction. According to Lenz's law, the EMF of self-induction always opposes any change in the current in the circuit and hence is generally termed as the back EMF. The total magnetic flux passing through a coil is proportional to the magnetic field, which in turn is proportional to the current I in the coil. Phi equals product of L and I. Here the proportionality constant L is called the self-inductance. According to Faraday's law, the induced EMF in the coil is given by minus L di by dt. Let us consider a long solenoid of cross-sectional area A and length L having n turns per unit length. Current I flow through the solenoid. The magnetic field set up inside the solenoid is given by the product of mu naught N and I. The magnetic flux through one turn of the solenoid is given by the product of mu naught N, I and A. The flux linkage in the solenoid with the total number of NL turns is given by mu naught N square ALI. Hence the self-inductance of the solenoid is given by mu naught N square AL. AC generator. The AC generator is an important practical device that operates on the principle of electromagnetic induction. It converts mechanical energy into electrical energy. It consists of a coil of wire that is mechanically rotated by some external means in a uniform magnetic field. As the coil rotates, the magnetic flux through it changes with time, inducing an EMF and a current in an external circuit. The ends of the coil are connected to the external circuit by means of slip rings that rotate with the coil. Each ring slides against a stationary carbon brush to which the external circuit is connected. The magnetic flux through a single turn of the coil at any time t is given by dot product of B and A, which is equal to BA cos theta. It can also be written as BA cos omega t. Here omega is the angular velocity and theta is the angle between the magnetic field vector and area vector. If the coil consists of n turns, the magnetic flux linkage in the coil is given by NBA cos omega t. According to Faraday's law, the induced EMF in the rotating coil is given by NBA omega sin omega t, or it can be written as E is equal to EM sin omega t, where EM is equal to NBA omega is the maximum value of the EMF. The induced EMF varies sinusoidally with time. Did you know? If the magnet is rotated about its axis, there is no change of magnetic flux linked with the loop and hence no EMF will induce. In dithermy process, we make use of eddy currents for the localized heating of tissues in human body. In coin-operated vending machines, eddy currents are used to detect counterfeit coins. Summary. Let us summarize what we have learned. The phenomenon of producing an induced EMF with the help of a magnetic field is called electromagnetic induction. Only relative motion between the magnet and the coil is required to produce the current. Magnetic flux is a measure of the quantity of magnetism, being the total number of magnetic lines of force passing through a specified area in a magnetic field. Lenz's law states that the direction of the induced EMF or induced current is such that it opposes the change that is producing it. Induced EMF can also be produced by moving a conductor inside a uniform magnetic field. Eddy current is defined as currents induced in a thick conductor when the conductor is placed in a changing magnetic field. The phenomenon in which a changing current in one circuit induces an EMF in another circuit is called mutual induction. The phenomenon in which a changing current in a circuit induces an EMF in the same circuit is called as self-induction. AC generator operates on the principle of electromagnetic induction. It converts mechanical energy into electrical energy.
तो मेरे प्यारे दोस्तों, ये था इलेक्ट्रोमैग्नेटिक इंडक्शन का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट। हेलो फ्यूचर डॉक्टर्स, कैसे हो सब? मैं हूं तुम्हारा बड़ा भाई, नीट ऑडियो मेंटोर। क्या तुम्हें भी ऑल्टरनेटिंग करंट AC और डायरेक्ट करंट DC के बीच का फर्क समझने में कंफ्यूजन होती है? क्या जब तुम ट्रांसफार्मर और LCR सर्किट्स के फॉर्मूलास देखते हो तो मुश्किल लगती है? तो चिंता मत करो दोस्त। इस वीडियो में हम इस चैप्टर के हर एक कॉन्सेप्ट को इतना आसान बनाएंगे कि तुम उससे कभी नहीं भूलोगे। लेकिन उससे पहले एक जरूरी बात, हमारे चैनल पर 97% लोग वीडियोस देखते हैं लेकिन सब्सक्राइब नहीं करते और सिर्फ 0.6% लोग हाई सब्सक्राइब करते हैं। यही वो लोग हैं जो कंसिस्टेंसी के साथ पढ़ते हैं और अच्छी कंटेंट की कदर करते हैं। इसलिए तुम्हें ये डिसाइड करना है, क्या तुम 97% की कैटेगरी में आते हो या 0.6% की कैटेगरी में जिनका सिलेक्शन होता है। तो अगर तुमने अभी तक इस चैनल को सब्सक्राइब नहीं किया है तो तुरंत सब्सक्राइब करो और इस बेल आइकन को भी दबाओ ताकि तुम्हारा कोई भी इंपॉर्टेंट लेक्चर मिस ना हो और तुम्हारी तैयारी पूरी हो सके। ओके।
Introduction. Hi Ram, how's you? I'm good, and what about you? Fine. What are you doing on laptop? I am just doing my physics assignment, alternating current. I will complete this in 10 to 15 minutes. Okay, I want to ask you something. Yeah, sure. You must know that laptop works on DC voltage as it has a battery, and laptop gets charged by plugging the charger in the AC voltage. My question is that, how is it possible that laptop works on the AC voltage?
I really don't know about that. Okay, let me tell you that laptops and many appliances also work on the DC voltage. When the charger is plugged into AC supply, then the charger converts the AC voltage into DC voltage so that the appliances can work smoothly.
Okay, I got it. It's interesting. Tell me more about it. Children, today we will study about the alternating current. Objectives. At the end of this lesson, you will be able to define alternating current, differentiate between alternating and direct current, calculate AC voltage applied to a resistor, calculate root mean square value of current and voltage, calculate AC voltage applied to an inductor and capacitor, define inductive reactance and capacitative reactance. Definition. An AC generator produces an alternating voltage that varies sinusoidally with time. Such a voltage is called an AC voltage, and the current driven by it in a circuit is called an AC current. The electrical main supply in our homes and most of the electrical appliances we use today require AC voltage. The main reason for preferring use of AC voltage is that it can be changed conveniently and efficiently to either higher or lower amplitudes by means of a transformer. Alternating current or voltage. The conditions for a periodically varying current or voltage to be termed as alternating are following. Every cycle corresponding to one time period has half positive and half negative value alternately. In case of current, it means that direction of current reverses after every half cycle, and in case of voltages, it means that the polarity of potential difference reverses after every half cycle. The positive and negative half cycles are exactly symmetrical. The amplitude of current or voltage on both positive and negative sides remains constant in all cycles. Difference between alternating and direct current. AC cannot produce chemical effects of current, but DC can produce chemical effect of current such as electroplating or electrolysis. AC can be stepped up or stepped down by transformers, but transformer is of no use for DC. AC can be converted into DC by using electronic rectifiers, whereas DC can be converted into AC by inverters. AC voltage applied to a resistor. We consider a circuit consisting of a resistor of resistance R and an AC EMF source. The AC voltage across the terminals of the source varies sinusoidally with time according as V is equal to Vm sin omega t, where Vm is the amplitude of the alternating voltage and omega is the angular frequency. We apply Kirchhoff's rule in the loop to get I is equal to Vm upon R multiplied by sin omega t. The maximum current given by Vm upon R. Now, the above equation can be written as I is equal to Im sin omega t. At any instant, the voltage across the resistor is given by Vr is equal to IR. By putting the value of I, we get Vr is equal to Vm sin omega t. Above equation show that in an AC circuit, the current through a resistor is in phase with the voltage across its terminals. Root mean square value of current and voltage. Let us consider the sinusoidal voltage and current given by V is equal to Vm sin omega t. I is equal to Im sin omega t. Both V and I are positive for one half of the cycle and negative in the other half. Therefore, the average value of a complete cycle is 0. Root mean square current. The square root of the average value of the square of the current is called the root mean square, RMS current. IRMS is equal to Im upon root 2, which is equal to 0.707 Im. In the same way, the RMS voltage is related to the maximum value of the alternating voltage. VRMS is equal to Vm upon root 2, which is equal to 0.707 Vm. The resistance R in a purely resistive circuit has the same value at all frequencies. A graph of resistance versus angular frequency is a horizontal
Straight line.
example on instantaneous voltage. Let's take an example on instantaneous voltage. The electrical mains in a house are marked 220 volt, 50 Hz. Write down the equation for instantaneous voltage. Let's see the solution. Given values are EV is equal to 220 volt. Nu is equal to 50 Hz. We know that EV is equal to E naught divided by root 2, or E naught is equal to root 2 EV. On putting the values in the equation, we get E naught is equal to 311 volt. Also, we know that omega is equal to 2 pi nu. On putting the values in the equation, we get omega is equal to 314 radian per second. Hence, the instantaneous voltage is given by E is equal to 311 sine 314 t. Power delivered to a resistor. The instantaneous power supplied to the resistor is given by PR is equal to VI, which is equal to the product of Vm sine omega t and Im sine omega t. It can be written as PR is equal to product of Vm, Im and sine square omega t. The average power supplied in one complete cycle is given by PR is equal to Vm multiplied by Im divided by 2. Since the time average of sine square omega t over a complete cycle is 1 by 2, it can be written as PR is equal to Vrms into Irms, or PR is equal to Irms square into R. Representation of AC current and voltage by rotating vectors. The phase relationship between the current and voltage in an AC circuit can be easily determined by using a technique which involves phasors. The diagrams containing phasors are called phasor diagrams. In this technique, voltage and current that varies sinusoidally with time are represented by rotating vectors V and I called phasors, whose length represent the maximum voltage Vm and maximum current Im. Consider the phasor diagram for an AC resistor circuit. The phasors V and I are collinear as they rotate because the voltage and current are in phase. At time t, the phasors make an angle omega t with the positive x-axis. AC voltage applied to an inductor. Consider an AC circuit consisting only of an inductor of inductance L connected to an AC source. The AC voltage across the source is equal to Vm sine omega t. The changing current output of the AC source produces a back EMF in the coil of magnitude given by VL is equal to L di by dt. We apply Kirchhoff's rule in the loop to get V minus VL is equal to 0. Now, put the values in the above equation. di by dt is equal to Vm upon L multiplied by sin omega t. Now, integrating both sides with respect to time, we get I is equal to Im sin omega t minus pi by 2. The amplitude of the oscillating current is written as Im is equal to Vm upon omega L. Inductive reactance. Inductive reactance. From the expression Vm upon omega L, we see that the quantity omega L plays the same role of resistance and is called the inductive reactance of the inductor, denoted by XL. XL is equal to omega L. The amplitude of the current in a purely inductive circuit is given by Im is equal to Vm upon XL. Power delivered to an inductor. The instantaneous power supplied to the inductor is given by negative Vm Im by 2 multiplied by sin 2 omega t. Since the time average of sin 2 omega t over a complete cycle is 0, therefore, inductor power is equal to 0. Phasor diagram of an inductive circuit. Phasor diagram. In an AC circuit, the current through an inductor lags the voltage across its terminals by pi by 2. At the points on the current graph where the current is 0, the graph is at its steepest and the current has the largest rate of increase or decrease. Thus, voltage and current are not in phase, but are 1/4 of a wave cycle out of phase. AC voltage applied to a capacitor. Consider an AC circuit consisting of a capacitor of capacitance C and an AC source. The AC voltage across the source is V is equal to Vm sin omega t. If Q be the charge on the capacitor at any time t, then the instantaneous voltage across the capacitor is given by Vc is equal to Q divided by C. We apply Kirchhoff's rule in the loop to get V minus Vc is equal to 0. Now we put the value in the above equation. Vc is equal to Vm sin omega t. The instantaneous current in the circuit is given by Im sin omega t plus pi by 2, where Im is equal to omega c. Vm is the amplitude of the oscillating current. Capacitive reactance. Capacitive reactance. The above expression Im is equal to omega c Vm can also be written as Im is equal to Vm divided by 1 upon omega c. The capacitive reactance Xc of the capacitor is given by 1 upon omega c. The amplitude of the current in a purely capacitative circuit is given by Im is equal to Vm upon Xc, or Irms is equal to Vrms upon Xc. Power delivered to a capacitor. The instantaneous power supplied to a capacitor is given by Vm Im upon 2 multiplied by sin 2 omega t. Since the time average of sine 2 omega t over a complete cycle is 0. Therefore, capacitor power is equal to 0. Phasor diagram of a capacitive circuit. Phasor diagram. In an AC circuit, the current through a capacitor leads the voltage across its terminals by pi by 2. When voltage increases from A to B, the charge on the capacitor increases and reaches its full value at B. However, the current representing the rate of flow of charge has a maximum positive value at the start of the charging process at A dash. While the capacitor voltage decreases from B to C, the charges flow out of the capacitor in a direction opposite to that of the charging current, as indicated by the negative current from B dash to C dash. Thus, voltage and current are 1/4 wave cycle out of step. Did you know? The first alternator to produce alternating current was a dynamo-electric generator based on Michael Faraday's principles constructed by the French instrument maker Hippolyte Pixii in 1832. Inductor cannot reduce direct current. It can reduce only alternating current. Capacitor allows alternating current to flow through it, but blocks direct current. Summary. Let us summarize what we have learned. An AC generator produces an alternating voltage that varies sinusoidally with time. In an alternating current, every cycle corresponding to one time period has half positive and half negative value alternately. In an AC circuit, the current through a resistor is in phase with the voltage across its terminals. The square root of the average value of the square of the current is called the root mean square current. In phasor diagram, voltage and current that varies sinusoidally with time are represented by rotating vectors V and I called phasors, whose lengths represent the maximum voltage and maximum current. In an AC circuit, the current through an inductor lags the voltage across its terminals by pi by 2. In an AC circuit, the current through a capacitor leads the voltage across its terminals by pi by 2. Introduction. Mohan and his father are standing in the balcony. They are taking the fresh air in early morning. Mohan watching something towards roadside curiously. Father, what is that grey color box type mounted on the electricity pole? Son, that's a transformer. Okay, father. And why it is used? Please tell me. Son, it is used to lower down the voltage of electricity. Electricity produced at power station is of many thousands volt. This transformer lowered down the voltage to 220 volt for household and 440 volt for industrial purpose. Okay, father, and I want to know more about this. To know more about transformers, you have to explore the alternating current. Students, today we will study about the alternating current. Objectives. At the end of this lesson, you will be able to analyze series LCR circuit, represent impedance triangle, explain resonance in LCR circuit, describe sharpness of resonance in LCR circuit, calculate the power factor, describe LC oscillations, define transformers, understand types of transformers, explain energy losses in transformers. Series LCR circuit. Consider a circuit containing a resistor of resistance R, an inductor of inductance L, and a capacitor of capacitance C connected in series across an AC source. Let the source voltage is equals to Vm sin omega t. We apply Kirchhoff's rule in the loop to get V is equal to VR plus VL plus VC. The projection of VR at any instant on the vertical axis equals VR with its maximum value given by product of Im and R. The phasor VL leading the current phasor I by pi by 2 represents the voltage across the inductor. Its projection on the vertical axis at any instant equals VL with its maximum value given by product of Im and XL. The phasor VC lagging the current phasor I by pi by 2 represents the voltage across the capacitor. Its projection on the vertical axis at any instant equals Vc with its maximum value given by product of Im and Xc. Now, we add the voltage phasors VR, VL and Vc vectorially to get the phasor V representing the net voltage across the circuit. V maximum is equal to under root of VR maximum square plus Vc maximum minus VL maximum square. The right triangle gives the equation for the maximum value of the net voltage and the phase angle. Tan phi is equal to Vc maximum minus VL maximum upon VR maximum. By using Ohm's law, we get Vm is equal to Im multiplied by under root of R square plus Xc minus XL square. We get the impedance of the circuit given by under root of R square plus Xc minus XL square. Now, the above equation becomes Vm is equal to product of Im and Z. We can also write this equation as Im is equal to Vm upon Z or IRMS is equal to Vrms upon Z. Phasor diagram solution of series LCR circuit. The instantaneous current has the same value at all points of the circuit. I is equal to Im sin omega t plus phi, where phi is the phase difference between the voltage across the source and the current in the circuit. The instantaneous voltage across the three elements have the following phase reactions to the instantaneous current. The instantaneous voltage across the resistor VR is in phase with the instantaneous current I. The instantaneous voltage across the inductor VL leads the current I by pi by 2. The instantaneous voltage across the capacitor VC lags the current I by pi by 2. Impedance triangle. Impedance triangle can be used to calculate impedance when resistance, inductance and capacitance all are present in the circuit and the total reactance is the difference between the inductive reactance and capacitive reactance. Z is equal to under root of R square plus XC minus XL square. A right triangle with the impedance Z as its hypotenuse, the quantity XL minus XC is called the reactance of the circuit, denoted by X. Tan phi is equal to XC minus XL upon R. Resonance in LCR circuit. Resonance occurs in systems which have a tendency to oscillate at a particular frequency when a periodic external force whose frequency exactly equals this natural frequency is applied to the system. At resonance, the energy delivered by the external periodic force to the system is at the maximum rate possible, resulting in a large amplitude oscillatory motion of the system. The frequency omega naught at which the current amplitude becomes maximum is called the resonant frequency of the circuit. Omega naught is equal to 1 upon under root LC. At resonance, the amplitude of the current oscillations is determined entirely by the resistance R. Im max is equal to Vm upon R. At resonance, the instantaneous current I and the voltage V in LCR circuit are in phase. Sharpness of resonance in LCR circuit. The effect of resistance on electrical resonance is to make the sharpness of the resonance curve less pronounced. The smaller the resistance, the sharper is the resonance curve. The quality factor Q of the circuit is given by omega naught L upon R or 1 upon omega naught CR. Quality factor is used to describe the sharpness of resonance peaks. If R is small or L is large, the quality factor Q is large, signifying that the resonance is sharper and the circuit is more selective. Example. Let's take an example of resonance in LCR circuit. Obtain the resonant frequency and Q factor of a series of LCR circuit with L is equal to 3 Henry, C is equal to 27 microfarad and R is equal to 7.4 ohm. It is desired to improve the sharpness of the circuit by reducing its full width at half maximum by a factor 2. Let's see the solution. Given values are L is equal to 3 Henry, C is equal to 27 into 10 raised to the power minus 6 farad, R is equal to 7.4 ohm. We know that resonance frequency is given by 1 upon under root LC. Now, putting the values and we get resonance frequency equals to 111 radian per second. Q factor is equal to omega R L upon R. Now, putting the values and we get Q factor equals to 45. As Q is inversely proportional to R, so R should be halved in order to double Q. The power factor. We know that an AC voltage V is equal to Vm sin omega t applied across an LCR series circuit drives a current in the circuit given by Im sin omega t plus phi. The instantaneous power dissipated in the circuit is P is equal to Vi. The time average of the power over a complete cycle is given by Vrms into Irms into cos phi. We can conclude that the average power delivered to the circuit depends not only on the voltage and current, but also on the cosine of the phase angle phi between them. The term cos phi is called the power factor of the circuit. From the impedance diagram, we can define the power factor as cos phi is equal to R upon Z, which is equal to R upon under root R square plus XL minus XC square. Now, we are using both above equations to calculate time average of the power over the complete cycle. P bar is equal to product of IRMS square and R. Power factor in different circuits. Case 1. Resistive circuit. If the circuit contains only the resistor, then phi is equal to 0. Value of cos phi is equal to 1. There is maximum power dissipation. P bar is equal to product of Vrms and Irms. Case 2. Purely inductive or capacitative circuit. If the circuit contains only the inductor or capacitor, then phi is equal to minus pi by 2 or pi by 2. Value of cos phi is equal to 0. There is no power dissipation. P bar is equal to 0. Case 3. LCR series circuit. If the circuit contains the inductor, capacitor and resistor, then cos phi lies between 0 and 1. there is always power dissipation in the circuit. P bar is equal to product of Vrms, Irms and cos phi. Case 4. Power dissipated at resonance in LCR circuit. Power is only dissipated in the resistor. No power is dissipated as heat by either an inductor or a capacitor in an LCR circuit. LC oscillations. We assume that initially the capacitor C of the LC circuit carries a charge Q and the current I in the inductor is 0. At that time, the energy stored in the electric field of the capacitor is UE and the energy stored in the inductor UB is 0. The capacitor now begins to discharge through the inductor. The current begins to flow anti-clockwise. The charge on the capacitor decreases, but the energy in the magnetic field of the inductor increases. The energy is transferred from the capacitor to the inductor. The energy stored in the capacitor is transferred entirely to the magnetic field of the inductor. At this stage, there is maximum value of current in the inductor. Now, energy flows from the inductor back to the capacitor as the electric field builds up again. Complete transfer of energy takes place from inductor to the capacitor. This situation is just like the initial situation except that the capacitor is charged oppositely. The capacitor will begin to discharge again. The current will now flow in clockwise direction. The energy stored in the capacitor is transferred entirely to the magnetic field of the inductor. Energy now flows from the inductor back to the capacitor. The energy is continuously shuttled back and forth between the electric field in the capacitor and the magnetic field in the inductor. The process continues at a definite frequency V. If no resistance is present in LC circuit, then the LC oscillations will continue indefinitely. Transformers. A transformer is a device used to lower or raise the amplitude of AC voltage and current. A transformer consists of a soft iron core on which two coils of wire are wound. One is called the primary with NP turns and the other is called the secondary with NS turns. The primary is connected to the AC EMF source. The secondary provides the output of the transformer. The soft iron core is used to increase the magnetic flux and to provide a medium in which nearly all the flux through one coil passes through the other. The flux through the primary and secondary is also changing, and hence an EMF is induced in both coils. Working of transformer. When an input AC voltage is applied to the primary, the alternating current in it establishes a changing magnetic field in the iron core. Since the magnetic field is changing, the flux through the primary and secondary is also changing, and hence an EMF is induced in both coils. Let phi is the magnetic flux through each turn of both the coils. The induced EMF in the secondary is due to mutual induction. ES is equal to minus NS d phi by dt. The induced EMF in the primary coil arises from self-induction. EP is equal to minus NP d phi by dt. Now, dividing both the equations, we get ES by EP is equal to NS by NP. This equation is known as the transformer equation. It can be written in the form of terminal voltage as Vs by Vp is equal to Ns by Np. The ratio Ns by Np is called the turns ratio of the transformer. Types of transformers. Transformers are of following two types. Step-up transformer. When the secondary voltage is greater than the primary voltage, the transformer is referred to as a step-up transformer. Step-down transformer. When the secondary voltage is less than the primary voltage, the transformer is referred to as a step-down transformer. A transformer that steps up the voltage simultaneously steps down the current, and a transformer that steps down the voltage steps up the current. Is by Ip is equal to Vp by Vs is equal to Np by Ns. Application of transformer. It is used to increase voltage before transmitting electrical energy over long distance through wires. They have shaped the electricity supply industry, permitting generation to be located remotely from points of demand. They are also used extensively in electronic products to step down the supply voltage to a level suitable for the low voltage circuits they contain. Signal and audio transformers are used to couple stages of amplifiers and to match devices such as microphones and record players to the input of amplifiers. Audio transformers allowed telephone circuits to carry on a two-way conversation over a single pair of wires. Energy losses in transformer. There are some energy losses in transformer as following. Flux leakage. Energy is lost when not all the flux produced by the primary pass through the secondary. This loss can be reduced by winding the primary and secondary coils one over the other. Resistance of the windings. Energy is lost due to the heat produced in the windings. This loss can be reduced by using thick wires. Eddy currents. Energy in the form of heat is lost due to the eddy currents in the iron core. This loss is reduced by using laminated core. Hysteresis. Energy is also lost in the form of heat during the cycles of magnetization and demagnetization of the iron core. This loss can be minimized by using core material having narrow hysteresis loop. The use of soft iron core limits hysteresis loss and flux leakage. Did you know? Parallel resonant circuit can be used as a rejector or filter circuit. Such circuits are used in radio transmitters. A capacitor could produce electrical oscillations was discovered in 1826 by French scientist Félix Savary. Radio frequency transformers are designed to operate efficiently within a narrow range of high frequencies. Summary. Let us summarize what we have learned. In series LCR circuit, the instantaneous voltage across the resistor is in phase with the instantaneous current. The instantaneous voltage across the inductor leads the current by pi by 2. The instantaneous voltage across the capacitor lags the current by pi by 2. Impedance triangle is used to calculate impedance when resistance, inductance and capacitance all are present in the circuit. At resonance, the energy delivered by the external periodic force to the system is at the maximum rate possible, resulting in a large amplitude oscillatory motion of the system. At resonance, the instantaneous current I and the voltage V in the LCR circuit are in phase. A transformer is a device used to lower or raise the amplitude of AC voltage and current. In transformer, energy is lost due to the heat produced in the windings. This loss can be reduced by using thick wires. The use of soft iron core limits hysteresis loss and flux leakage.
तो मेरे प्यारे दोस्तों, ये था ऑल्टरनेटिंग करंट का एक कॉम्प्रिहेंसिव लेक्चर। हमने हर कॉन्सेप्ट को जीरो से समझा है। एनिमेटेड वीडियोस आ रही है, जिसमें हम इन सभी टॉपिक्स को और भी अच्छे से समझेंगे। उनके लिए प्लेलिस्ट को चेक करते रहना, लिंक डिस्क्रिप्शन में है। दोस्तों, हमारी टीम ने आपके लिए क्लास 11th की पूरी बायोलॉजी, बॉटनी और जूलॉजी और पूरी क्लास 11th फिजिक्स कंप्लीट कर दी है। इसलिए तुम्हें NEET की तैयारी के लिए कहीं और जाने की जरूरत नहीं है। तुमने इस वीडियो को शुरू से लेकर एंड तक देखा, इसका मतलब तुम वो 0.6% वाली कैटेगरी में आते हो जो सिलेक्शन लेते हैं। चलो पढ़ते रहो, मेहनत करते रहो और अपने सपनों को पूरा करो। ऑल द बेस्ट।
Yeah!